that the Department of Mathematics serves as a national in collaboration with the Wade Institution for Mathematical Science is organizing an international conference on mathematical analysis and interpretation, conducting a conference in the area of mathematics and attracting academicians nationally and internationally to participate is truly an achievement. I appreciate the progress of the department and wish it well on its journey of excellence. I am thankful to the organizers of the conference and the conference chair, Dr. S.P. Shetty, to give me a chance to participate in this conference. Here is the outline of my talk. I am going to start with the introduction of mathematical method, creed, and composite. Then I will come to study the creed behavior, operating composite base, operating under various types of temperature predictions. First of all, let me explain what is mathematical value, what is creed, and what are composites. After that, we will see how the thermal gauge conditions can affect the creed or taking this. Let's start with mathematical model. You have seen that much of our progress in the last 2 centuries has made it necessary to apply mathematical methods to real-life problems arising from the universe. The use of mathematics in solving real-world problems has become quite extensive, especially due to increased computational powers of digital computers and computing methods available to us, both of which have facilitated the handling of lengthy and complicated problems. The process of translation of a real-life problem into a mathematical form can give a better representation and solution of certain problems. This process of translation is called mathematical modeling. For modeling, the first step is to understand the problem and to find the relevant factors or essential parameters involved in the problem. The next step is to find an equation or an inequality or a geometric figure using the parameters already identified. Then, to find the solution of the problem, one has to do some mathematical operations which involve solving an equation, calculations, or applying methods or theorems already exist. Many times, model equations are obtained by assuming a situation in an idealized context. The model will be useful if it explains all the facts that one would like to explain. Otherwise, one will reject it or else improve it and test it again. Under many service conditions, materials are required to sustain steady loads for prolonged periods of time under different temperature conditions. For example, furnace parts, blades of turbine rotors, timber beams in the roofs of the buildings, filaments in vacuum tubes, etc. Under these conditions, material may continue to deform until its usefulness is seriously impaired. Such time-dependent deformations can grow large and result in fracture of the member without any increase in load. This time-dependent strain occurring under constant stress is known as creep. Creep may be defined as a process by which plastic flow occurs when a constant stress is applied for a prolonged period of time. Creep can take place and lead to fractures at static stresses much smaller than those which will break the specimen when loaded quickly. Synthetic ropes will elongate when loaded over a long period of time. This phenomena is known as creep. When metal matrix composites are tested under creep conditions using tensile or shear configurations, it is usually possible to identify the standard three distinct stages of flow within the creep curve. One is primary creep, the other one is a secondary creep, and the third one is tertiary creep. A creep curve is a plot between the total creep and the time for the entire duration of test. There is generally a normal primary stage known as transient creep, in which the strain rate decreases with increasing time, and this is followed by a brief secondary stage where the strain rate remains reasonably constant. This stage is now known as steady state creep. And then comes an extended tertiary stage where the strain rate increases with time until fracture occurs. The given figure shows a creep curve and marks the various stages of creep. Although it was recognized that the secondary stage was very short by comparison with most pure metals and solid solution alloys, by contrast, some metal matrix composites exhibit creep curves where the secondary stage was more linearly delineated. The close similarities in the creep curves of unreinforced powder metallurgy materials and metal matrix composites provide support for analytical or theoretical treatment of creep results for metal matrix composites in terms of the steady state creep rates. Many engineering applications provide severe thermomechanical loading because of simultaneous presence of high thermal gradients and loads, where the conventional materials like metals or ceramics alone may not be suitable.
Very high loads or high temperature will accelerate the creep process. The combination of these three factors, load, temperature and time, determines whether creep is relevant for a particular problem or not.
The growth of technology has placed rather severe demands on material engineers to come up with novel materials at low cost to meet stringent and often contradictory property requirements which conventional materials cannot satisfy. In this respect, composite materials show great promise. These are the materials which are tailored by combining two or more materials to get properties that are not attainable by any of its constituents alone.
Let's take a closer look at its structure. It has at least two different materials whose properties complement each other. These materials contain either dispersed fiber, particles, embedded in a matrix, which may be metallic, polymer, or a ceramic material. Metal matrix composites are based on metals or metal alloys reinforced with fibers, particles, or whiskers. Metal matrix composites containing particles and whiskers are generally isotropic and are relatively cheap. The composites might contain aligned continuous, aligned discontinuous, or random fibers, particles, or whiskers of ceramic materials like silicon carbide, alumina, etc. in a matrix which may be a metal or an alloy. Because of their superior stiffness, high strength at elevated temperatures, and better creep characteristics, metal matrix composites are finding increasing applications in components exposed to elevated temperatures. Thus, composite material is a combination of two or more micro-constituents differing in the form and are essentially insoluble in each other. They are different from alloys. Two or more materials with different physical and chemical properties are combined to create a specialized material required to do a particular job. They improve the properties of their base materials and are applicable in many situations. The concept of functionally graded materials emerged and led to the development of superior heat resistant materials while keeping the cost under control. FGMs are special types of composites containing inhomogeneous distribution of constituents like heat-resistant ceramics on the higher temperature side and tough metals with high thermal conductivity on the lower temperature side, so designed to withstand severe thermomechanical loading. These materials have been developed as ultra high temperature resistance materials for potential applications in aircrafts, space vehicles, and other products working at elevated temperatures. In addition to excellent mechanical and thermal properties, FGMs also possess the advantage of optimizing the use of costly dispersoids as the composition of dispersoids in FGMs changes from the high temperature region to the low temperature region. Mechanical properties of composite depend substantially on the processing and fabrication methods used, as well as on the fiber orientation.
The major advantage of functionally graded materials is the possibility of tailoring its gradation to maximize its performance.
Safety and efficiency are non-negotiable in modern shipping. The number one choice for mooring lines is Dyneema company. Fibers from Dyneema have been proven to have lowest creep rate and longest lifetime. Now let's start with the steady state creep of composite rotating disc. Rotating disc is a commonly encountered component in aero engines, automobiles, turbines, pumps, compressors, flywheels, and in a number of other dynamic applications. Many of these applications are exposed to elevated temperatures where creep deformation becomes important. The enhanced creep of lightweight aluminium and its alloys may not permit their application at elevated temperatures. From this point of view, components based on metal matrix composites with aluminium or aluminium alloys reinforced with ceramic, fibers, viscose, putty plates are found to be extremely useful. Experimental studies have demonstrated that steady state creep rate in aluminium or its alloys may be reduced by several orders of magnitude when it is reinforced with ceramic particles or viscose like silicon carbide. Any research work on composites should therefore attempt to analyze creep in structural components like rotating disc made of lightweight aluminium, ceramic, composite so as to develop more reliable design codes for real-life applications. Creep is of extreme technological significance since it limits the use of modern materials in a number of applications such as automotive, engines, and components of aerospace and power generation plants. Superior mechanical properties and high strength to weight ratio of such materials have led to an increased interest in the automobile and aerospace industries, in which saving the weight of component is a critical issue. The prediction and analysis of creep properties to assess service life of engineering components made of composites is of great help for practicing engineers. Several fabrication techniques have been developed in recent years to manufacture the composites with specific properties in mind. The aluminium matrix can be reinforced with a variety of ceramic particles of different shapes and sizes to achieve the desired properties. This motivates us to do work on steady state creep of a rotating disc.
Let us consider an annular disc of aluminium matrix reinforced with silicon carbide particulates having inner radius A to be 0.03175 meters and outer radius B to be 0.1524 meters. The particulate size of the material is denoted by P be taken as 1.7 micrometers and the volume fraction of the reinforcement denoted by V is considered to be 10 volume percent fraction of the constituent material. The density variation in the composite is expressed by the law of mixture formula, where rho subscript m equal to 2713 kilograms per cubic meter is the density of the matrix alloy, and rho subscript d taken equal to 3210 kilograms per cubic meter represents the density of the dispersed silicon carbide particulates. For the present study, the discs with three temperature profiles have been considered. Disc with uniform temperature profile D subscript 100 is operating at uniform temperature of 623 Kelvin along the radial distance. Three different discs operating under linearly decreasing distinct thermal gradients are represented by T superscript 1 subscript 101, D superscript 2 subscript 101 and D superscript 3 subscript 101 having temperature distribution T depending upon radius denoted by A minus BR, where the values of A and B can be calculated using the values of inner radius, outer radius and temperatures at inner radius and outer radius of the disc. For nonlinear profile, three discs operating under parabolically decreasing temperature distribution T have been considered, where T is given by C minus D R square, where the value of C and D can be calculated similarly using the values of inner radius, outer radius, temperatures at inner radius and outer radius. For various composite discs under various thermal gradation profiles, the values of temperature at inner radius and temperature at outer radius for discs are given in this table. We can take the value of operating temperature conditions according to the given table for uniform, linear and nonlinear temperature profiles.
The steady state creep response of the aluminium silicon carbide particulate composite has been described by Sherby's constitutive model, which gives the relation between the strain rate, effective stress, threshold stress and creep parameter. Effective strain rate under biaxial stress is denoted by epsilon bar dot. Effective stress under biaxial stress is denoted by sigma bar. Threshold stress is denoted by sigma naught and creep parameter by m. In a particle reinforced composite, the creep parameters m and sigma naught depend on the particle size P and the particle content V apart from the temperature T. The creep parameters m and sigma naught had been obtained from the creep results reported by Pandey in 1992 for aluminium silicon carbide composite under uniaxial loading. The values of the creep parameters m and sigma naught as function of material parameters P, V and T have been calculated through software data fit using following regression equations. For symmetry considerations, principal stresses are taken along radial, tangential and axial directions for the composite disk having uniform thickness h rotating with angular velocity omega. For the purpose of modeling, we assume that steady state condition of stress. We assume the elastic deformations are small for the disk and can be neglected as compared to the creep deformations. We also assume the biaxial state of stress exists at any point of the disk. Taking reference frame along the radial, tangential and axial directions, the generalized relation for the creep in isotropic rotating disk is given by radial strain rate, tangential strain rate and axial strain rate in terms of effective strain rate, effective stress, radial stress, tangential stress and axial stress, where the effective stress is calculated using von Mises yield criteria as given in the formula. For biaxial state of stress, axial stress can be neglected and the effective stress is given in terms of radial and tangential stresses only. Further, substituting the value of effective strain rate from Sherby's constitutive model in the generalized constitutive equations, we get the following constitutive equations in terms of effective stress, threshold stress and x, where x is the ratio of radial to tangential stress and here UR is the radial displacement.
Equations 14 and 15 of radial strain rate and tangential strain rate respectively from previous constitutive equations be solved to obtain tangential stress sigma theta in terms of radial displacement rate at A, creep parameter m, psi 1 and psi 2. Here radial displacement rate at A can be calculated using the given formula in terms of psi 1 and psi 2, where psi 1 and psi 2 be further calculated using psi and sigma naught. Here psi be calculated using phi as given in the expression where phi can be calculated using 2x minus 1 divided by 2 minus x. Here x represents the ratio of radial stress to tangential stress.
The equation of motion for a rotating disk of uniform thickness h may be obtained by considering the equilibrium of an element in the composite disk confined between radial distance r and r plus dr and an interval of angle between theta and theta plus d theta. The equilibrium of forces in the radial direction of the element under assumed conditions gives the following equation of equilibrium. Knowing the tangential stress distribution sigma theta from the previous equation, values of sigma r, that is radial strain along the radius, can be obtained using the given formula. Thus, knowing the values of radial and tangential stresses, we can calculate the radial, tangential and axial strain rates from the constitutive relations already given by equation
numbers 14, 15 and 16 respectively.
An iterative solution technique can be employed using the boundary conditions that radial stresses at inner and outer boundaries should be zero. The stress distributions is evaluated from the above analysis by iterative numerical scheme of computations. The iterations are continued till the process converges, yield the values of stress at different points of the radius grid. For rapid convergence, 75% of the value of tangential stress obtained in the current iteration has been mixed with 25% of the value of tangential stress obtained in the last iteration for the use in the next iteration as shown. Numerical computation has been done to obtain the steady state creep response of the disks having particle size P equal to 1.7 micrometer and particle content V equal to 10 volume percent of the aluminum silicon carbide particulate. In order to validate the developed computer program, the results for our rotating steel disk were obtained and compared with the available experimental results of Wall, which performed the experiment in 1954 for the same type of disk and operating under same conditions as mentioned in the table. The comparison of present theoretical work and Wall's experimental work done in 1954 for strain rates versus radial distance is shown graphically in the given figure. This graph depicts that there is a good agreement between the present theoretical work and Wall's experimental results for radial strain rates versus radial distance. The tangential strain rates also follow the same trends for present work as well as Wall's experimental results throughout the radial distance. A good agreement and similar trends observed between the present theoretical and Wall's experiment strain rates inspire the confidence in us. Based on the above mathematical formulation, a computer code in MATLAB has been generated to calculate the steady state creep behavior of the disks subjected to uniform, linear and non-linear thermal gradation. Results are compared graphically to study the effect of thermal gradient at elevated temperatures. Figure shows the variation of radial stress, tangential stress, radial strain rates and tangential strain rates along radial distance in the disk with uniform profile, linear and non-linear profiles having temperature gradient of 0 Kelvin, 24.63 Kelvin and 30 Kelvin. We can see clearly from the figure A that as one moves radially outwards from inner radius, the radial stress increases from 0, reaches a maximum value near the middle of the disk and then decreases to 0 towards the outer radii for all the above said disks. The value of radial stresses for disk D100 having uniform temperature along the radius shows very minor reduction as compared to disk D101 and 102 having decreasing linear and non-linear temperature gradation respectively. Further, effect of different temperature profile on tangential stresses as shown in the figure B is very small. The graph shows that the tangential stresses increases from inner radius, attain maximum values and then decreases as one approaches outer radius. The tangential stresses is lowest for disk D100 with uniform profile and highest for disk D102 with non-uniform profile as compared to other disks. From the figure C, we can see that with the change in temperature distribution, the radial strain rate is affected significantly. For disks with linear and non-linear profiles, the radial strain rate decreases near the inner radius and increases near the outer radius in comparison to disks with uniform profile. Similarly, the tangential strain rates are also significantly affected with the change in temperature profile of the disk. Figure D clearly shows that the tangential strain rate decreases for disks with uniform, linear and non-linear profile as one moves from inner to outer radius. At the inner radius, the tangential strain rate has lowest value for disk with uniform profile in comparison to rest of the disk. And at the outer radius, the strain rate has lowest value for disk with non-uniform profile.
Figure 2 shows the variation of radial stress, tangential stress, radial strain rates and tangential strain rates along radial distance in the disk with the uniform profile, linear and nonlinear profiles for increased temperature gradients to 0 Kelvin, 49.25 Kelvin and 60 Kelvin respectively. We can see clearly from the figure 2a that similar trend follows like previously discussed graph 1a, that as one moves radially outwards from inner radius, the radial stress increases from 0, reaches a maximum value near the middle of the disk and then decreases to 0 towards the outer radii for all the above set disks as per boundary conditions applied. The value of radial stresses for disk 100 having uniform temperature along the radius shows very minor reduction as compared to disk 101 and 102 having decreasing linear and non-linear temperature gradations of 0 Kelvin, 40 Further, effect of different temperature profile on tangential stresses as shown in the given figure 2b is very small. The graph shows that the tangential stresses increases from inner radius, attain maximum values and then decreases as one approaches outer radius. The tangential stress is lowest for disk D100 with uniform profile and highest for disk 102 with non-uniform profile as compared to other disks. From the figure 2c, we can see clearly that with the change in temperature distribution, the radial strain rate is affected significantly for disks having increased temperature gradient of 0 Kelvin, 49.25 Kelvin and 60 Kelvin. For disks with linear and non-linear profiles, the radial strain rate decreases near the inner radius and on the other hand increases near the outer radius in comparison to disks with uniform profile. Here the tangential strain rates are also significantly affected with the change in temperature profile of the disk. Figure 2d clearly shows that the tangential strain rate decreases for disks with uniform linear and non-linear profile as one moves from inner to outer radius. At the inner radius, the tangential strain rate has lowest value for disk with uniform profile in comparison to rest of the disks. And at the outer radius, The strain rate has lowest value for discs with non-uniform profile. With further increased temperature gradient to 0 Kelvin, 73.87 Kelvin and 90 Kelvin for disc with the uniform profile, linear and non-linear profiles, the results again shows the similar trends as already discussed for figure 1 and figure 2 for radial as well as tangential stresses and strain rates. It can see clearly from the figure 3a that similar trend follows like previously discussed graphs 1a and 2a. That as one moves radially outwards from inner radius, the radial stress increases from 0, reaches a maximum value near the middle of the disk and then decreases to 0 towards the outer radii for all the above set disks as per boundary conditions applied. The value of radial stresses for disk D100 having uniform temperature along the radius shows very minor reduction as compared to disk D101 and disk 102 having decreasing linear and non-linear temperature gradations of 0 Kelvin, 73.87 Kelvin and 90 Kelvin. Further, effect of different temperature profile on tangential stresses as shown in the given figure 3b is very small. The graph shows that the tangential stresses increases from inner radius, attain maximum values and then decreases as one approaches outer radius. The tangential stress is lowest for disk D100 with uniform profile and highest for disk D102 with non-uniform profile as compared to other disks. From the figure 3c, we can see clearly that with the change in temperature distribution, the radial strain rate is affected significantly for disks having increased temperature gradient of 0 Kelvin, 73.87 Kelvin and 90 Kelvin. For disks with linear and non-linear profiles, the radial strain rate decreases near the inner radius and on the other hand increases near the outer radius in comparison to disks with uniform profile. Here, the tangential strain rates are also significantly affected with the change in temperature profile of the disk. Figure 3d clearly shows that the tangential strain rate decreases for disks with uniform, linear and non-linear profile as one moves from inner to outer radius. At the inner radius, the tangential strain rate has lowest value for disks with uniform profile in comparison to rest of the disks, and at the outer radius, the strain rate has lowest value for disks with non-uniform profile. Now in this figure 4, the effect of different linear thermal gradients on radial stresses, tangential stresses, radial strain rates and tangential strain rates developed in rotating disks having linear temperature gradient of 23.63 Kelvin, 49.25 Kelvin and 73.87 Kelvin respectively are shown. Let us discuss its subgraphs one by one for disks with different linear thermal gradations. The effect of different linear thermal gradients on radial stresses developed in rotating disk 1, 2 and 3 having temperature gradient of 23.63 Kelvin, 49.23 Kelvin and 73.87 Kelvin respectively shown in the given figure 4a is very small. The effect of different linear thermal gradient on tangential stresses as shown in figure 4b is very small. The graph shows that the tangential stress attains values 81.69 megapascal, 81.32 megapascal and 80.94 megapascal at the inner radius respectively, then increases and attain maximum value of 87.75 megapascal, 87.40 megapascal and 86.71 megapascal at radial distance of 0.0559 meters for disk 3, disk 2 and disk 1 respectively, and again decreases to 66.05 megapascal as one approaches outer limits. The effect of different linear thermal gradients on radial strain rates can be seen near the inner and outer radii of the disk from the graph. The radial strain rates decreases with the decrease in thermal gradient in disk D1, D2 and D3 as shown in figure 4c. However, at the inner radius, disk D3 shows highest radial strain rate, and at the outer radius, radial strain rate is highest for disk D1. And the similar trends for tangential strain rates can be seen from the graph near the inner and outer radii for the effect of different linear thermal gradients. The tangential strain rates decreases with the decrease in thermal gradient in disks D1, D2 and D3 as seen in figure 4d. However, at the inner radius, disk D3 shows highest tangential strain rate, and at the outer radius, tangential strain rate is highest for disk 1. Thus, the tangential strain rate is highest for disk 3 at the inner radius and lowest for the same disk at the outer radius. As already discussed in figure 4, similar kind of variations of radial stress, tangential stress, radial strain rate and tangential strain rates along radial distance in disk with parabolic profiles having temperature gradient of 30 Kelvin, 60 Kelvin and 90 Kelvin can be seen from the graph of figure 5. Again, let us discuss its subgraphs one by one for disks with different parabolic thermal gradations. Once again, the effect of different parabolic thermal gradients on radial stresses developed in rotating disk 1, disk 2 and disk 3 having temperature gradient of 23.63 Kelvin, 49.23 Kelvin and 73.87 Kelvin respectively, shown in the given figure 5a, is very small. The effect of different parabolic thermal gradient on tangential stresses as shown in figure 5b is also very small. The graph shows that the tangential stress attains values 81.98 megapascal, 81.51 megapascal and 81.04 megapascal at the inner radius, then increases and attain maximum values of 88.15 megapascal, 87.67 megapascal and 87.19 megapascal at radial distance of 0.0559 meters for disk D3, D2 and D1 respectively, and again decreases to 66.05 megapascal as one approaches outer radius. As the thermal gradient increases, the tangential stresses also increases slightly. The effect of different parabolic thermal gradients on radial strain rates can be seen near the inner and outer radii of the disk from the graph. The radial strain rates decreases with the decrease in thermal gradient in disk 1, disk 2 and disk 3 as shown in figure 5c. However, at the inner radius, disk 3 shows highest radial strain rate, and at the outer radius, radial strain rate is highest for disk 1. And the similar trends for tangential strain rates can be seen from the graph near the inner and outer radii for the effect of different parabolic thermal gradients. The tangential strain rates decreases with the decrease in thermal gradient in disk 1, disk 2 and disk 3 as shown in figure 5d. However, at the inner radius, disk 3 shows highest tangential strain rate, and at the outer radius, tangential strain rate is highest for disk 1. Thus, the tangential strain rate is highest for disk 3 at the inner radius and lowest for the same disk at the outer radius.
As seen from the graphs, the strain rates are significantly affected with change in thermal gradient of the disk. So, the study of thermal gradient in rotating disks will give new insights to material engineers and designers. A significant improvement in specific strength and stiffness may be attained in these composites using variations in functionally gradient materials. Rotating disk is a commonly encountered component in aero engines, automobiles, turbines, pumps, compressors, flywheels, and in a number of other dynamic applications. Many of these applications are exposed to elevated temperatures where creep deformations become important. The enhanced creep of lightweight aluminium and its alloy may not permit their applications at elevated temperature. From this point of view, any research work on composites should therefore attempt to analyze creep in structural components like rotating disks made of lightweight aluminium ceramic composites so as to develop more reliable design codes for real-life applications. I would like to thank the audience for their kind patience, and once again I am thankful to the organizers of the conference.
S. Patil sir. Dr. Channabasangouda S. Patil sir is currently serving as a scientist E and director at the Aerodrome Meteorological Center, Kempegowda International Airport, Bangalore. He holds an MSc in physics with a first class from Karnatak University, Dharwad, and qualified the CSIR UGC NET in physics in December 2000. He joined the Indian Meteorological Department as a Group A officer through UPSC on 11th November 2002. His foundational education was in Kannada medium in Bagalkot district, and he completed his college studies at JSS College, Dharwad. Dr. Patil has been recognized by the Government of Karnataka and the State Disaster Management Authority for his accurate weather forecasts. Notably, he led the installation of 4 present weather detectors at Kempegowda Airport in December 2023. These advanced meteorological sensors report real-time weather conditions including precipitation, wind speed and direction, temperature and visibility. With this brief introduction, I would like to call Dr. Patil sir to chair the session.
Okay. Good morning, everybody. I am very happy to introduce Dr. A. Padmanabh Reddy. Dr. Padmanabh Reddy is a PGST young scientist and assistant professor in the Department of Mathematics at Vijayanagara Sri Krishna Devaraya University, Ballari in Karnataka state. With over a decade of experience since 2012, Dr. Reddy specializes in wavelet analysis, numerical analysis, differential equations and mathematical imaging. He has guided 7 PhD scholars and has completed a notable research project on wavelets and their scientific computing funded by the Karnataka government. He has published around 30 research articles in reputed journals and completed 4 NPTEL and SWAYAM certification course in advanced mathematical and data science topics. Dr. Reddy has been an invited speaker at over 30 national and international conferences and workshops, contributing significantly to mathematical research and education. Now he will speak. Thank you.
Thank you, Patil sir, for introducing in this gathering. So before starting my session, so I would like to thank organizing committee of this conference and especially Dr. Siraj Shetty sir for inviting me to present whatever little I understood to you. And this conference, and I advancedly congratulate Dr. Siraj Shetty for the for successful completion of this one conference. Next. So my title of the talk is A Study of Universal Approximation Theorem. So now slightly I shifted my research topics of interest from wavelets to neural networks, but it is not much difference. Okay. So anyway, so now I would like to, I am very much interested in, so because all the experts are very much familiar, and I want younger generation to understand this concept. Please, everyone, look at this one outside. Wherever you find doubt, I am ready to explain. So this is interaction, and this is not going to very geometric convenience to you. Everyone can understand what you mean by neural network. So they have put efforts in such a way that, so you are always welcome to pose a question. Oh, please, okay? Because this conference is meant for you. Okay. So So my outline of the talk is introduction. So the perceptron, working of perceptron, with illustration and various types of neurons, and learning means what you mean by learning. Next, neural nets can compute any function. Here in my talk, any function means continuous function. Any function means continuous function. Okay. So universal approximation theorem, for every theorem there is a limitation. I am going to address what are the limitations of UAT. Here UAT means universal approximation theorem. Any function means continuous function on a compact set. Okay. So summary and references. Okay. So now, how the coin is word artificial neuron. So, and we are familiar with biological neuron. Okay. So now this is the left hand side is the human nervous system, and this mimicked as a artificial neural network, ANN. So in any neural networks there are three types of layers. This one is nothing but input layer, this is nothing but hidden layer, this is nothing but output layer. Okay. In any artificial neural network there are three types of layers. One is input layer, hidden layer, and finally output layer. Okay. So now what do you mean by biological neuron? Here a biological neuron, also known as a nerve cell, is the fundamental unit of nervous system. Biological neuron is the fundamental unit of biological nervous system. Okay. So it is responsible, what is its role? It is responsible for receiving, processing and transmitting information through the electrical and chemical signals. These signals allow us for communication between different parts of the body, okay, and enables us sense, think and move. So we are going to receive signals from our brain through the biological neural network for actioning. What are our action? To talk or move from one place to another place. We are receiving signals from our brain through the biological network. So that one is imitated and coined as a artificial neural networks. Okay. So how the decision is taking place, I am going to explain with the examples. So now, same biological neuron is the fundamental unit for the biological neural network. Same thing, what is artificial neuron? Okay. It is a fundamental unit for artificial neural network. Okay. So now, some important components of the biological neuron. What are those? This is called soma or cell body, and these are called input units and dendrites. Okay. So dendrites act as the inputs, x1, x2, xn. These are all the inputs, and some processing work is taking place in the called soma or nerve cell. Once the processing has taken place, processing means we are going to understand something else. Next, once the processing taken place and we are putting some threshold on that one, taking decision, yes or no, like that, and based on the threshold or decision we are going to act. That is nothing but output. This output of one neuron may be input for another neuron. One output of one neuron may be input for the another neuron. This is a continuous. This is going to be act as a again input to this neuron. Okay. Here three parts: input, processing, output. For each neuron, three important concepts. What are those? Input, processing, output. Output of one neuron may be input for the another neuron. Okay. So now artificial neuron. Okay. An artificial neuron is a mathematical function conceived as a model of biological neuron. It is same like biological neuron. So the artificial neuron is elementary unit of artificial neural networks. In our biological neuron is biological neuron is a fundamental unit for biological neural network. That biological neuron is replaced by artificial neuron. Now onwards, just neuron means artificial neuron. Okay. So now, these are all the inputs. X1, it may have any number of inputs. It's a no condition. and these are all weights. These are processing work, how to initiate the processing work based on the weights. And this is called, is a part of processing work. These three: weights, transfer function, activation. These three comes under processing work. Okay? And this is the activation. We have to take decision or not based on our activation function. Okay. So structure of artificial neuron. So now same thing. This is the, in the final form, these are the four important parts in the biological. What are they called? Dendrites. Dendrites means inputs. Dendrites means input. Cell nucleus means node. Cell nucleus is also called soma. Okay? This is a node. Node or neuron. Axon, output. Axon outputs. Synapse means interconnection. This axon is going to be input for another neuron. These are called synapse, interconnections between one neuron to another neuron. So now what is perceptron? Now, what is the first fundamental unit is the neuron. That is how to take, what are the actions. It is, we have to take some models. We are considering nowadays perceptron. Okay? What do we mean by perceptron? A perceptron is an artificial neuron. It is the simplest possible neural network. In 1958, a psychologist called Frank Rosenblatt described the perceptron. Okay. Neural networks are building blocks for machine learning. Machine learning, deep learning. So these are the extension words of the perceptron. Okay. And everything depends upon the perceptron meaning. Okay. So now he is the person, Frank Rosenblatt. He is an American psychologist, notable in the field of artificial intelligence. Rosenblatt is the best known for the perceptron. An electronic, he has developed an IBM mission, okay, which imitates the biological neural network action. Okay. So now simple so one unit. Okay, good. So now these are all the unit x1, x2, x3 are the inputs, and this is the soma or nucleus. Processing takes place, and this is the output. Okay, x1, x2, x3, and this is the node, and this is the output. This is the simplest part of the perceptron. This will help us to understand neural network, machine learning, deep learning. Okay. Okay. Good. So perceptron takes binary inputs. Binary means, what do you mean by binary? What do you mean by binary? If you concentrate, answer is in the PPT itself. What do you mean by binary? Either 0 or 1. So inputs are x1, x2, x3. x1 is either 0 or 1. x2 is either 0 or 1. x3 is either 0 or 1. These are called binary inputs. Okay, good. So weights, W1, W2, W3. How many inputs? Those number of weights. Weights are maybe real numbers, but inputs are binary. Weights are real numbers. The neuron's output, again, either this is going to be binary. Input, output are binary, either 0 or 1. Weights are real numbers. Okay. So then this is the Wj are the weights, Xj are the input. X1 here either 0 or 1, Wj are the real numbers. This is called weighted sum. This is called weighted sum. This weighted sum exceeds the threshold. This weighted sum exceeds the threshold, output is 1. If this weighted sum less than the threshold, output is 0. Threshold number, which is parameter of the neuron output. So now this weighted sum is less than threshold 0. This of weighted sum is greater than threshold less than 1. Those who are working in the wavelets, they might know the threshold. So Please raise your hand, those who know the threshold. Threshold. Wavelets work ಯಾರು ಮಾಡಿರಿ? Threshold. Threshold means a cutoff. Threshold means cutoff. Below that cutoff, you are equating to 0. Above that cutoff, that one is going to be 1. This is the role of which one? Threshold. For example, if your result is first class, what is the cutoff? Result is first class. What is the cutoff? 60%. Suppose if your percent is 60 or greater than 60, your result is declared as a first class. Suppose less than 60%, your result is not a first class. That's all. This is called the cutoff or threshold. Okay. So will you go to concert? What do you mean by concert? It's a musical show. A concert means a musical show. So now, so try to understand this example. If you understand this example, neural network is, you can easily understand whatever follows. So this important example, nowhere mathematics, nowhere mathematics. Neenamma, up to, yes. What do you want? Ilban. So, ಒಂದು ಮ್ಯೂಸಿಕಲ್ ಶೋ ನಾನು ಅಟೆಂಡ್ ಆಗ್ಬೇಕಂದ್ರೆ, ಒಂದು ಮ್ಯೂಸಿಕಲ್ ಶೋ ನಾನು ಅಟೆಂಡ್ ಆಗ್ಬೇಕಂದ್ರೆ ನಿಮ್ಮ ತಲೆಗೆ ಏನೇನು ರನ್ ಆಗುತ್ತೆ? ಒಂದು ಮ್ಯೂಸಿಕಲ್ ಶೋ ನಾನು ಅಟೆಂಡ್ ಆಗ್ಬೇಕಂದ್ರೆ ನಿಮ್ಮ ತಲೆಗೆ ಏನೇನು ರನ್ ಆಗುತ್ತೆ? ವಾಟ್ ಇಸ್ ದ ಫಸ್ಟ್ ಒನ್? ಈಸ್ ದ ಆರ್ಟಿಸ್ಟ್ ಗುಡ್? ಅಂದರೆ ಮ್ಯೂಸಿಕಲ್ ಶೋ ಮಾಡೋರು ಅವನು ಪರ್ಫಾರ್ಮೆನ್ಸ್ ಚಲೋ ಇರ್ತತಾ ಇಲ್ಲ? ಎಸ್ ಸರ್. ಫಸ್ಟ್ ಪಾಯಿಂಟ್ ಈಸ್ ದ ಆರ್ಟಿಸ್ಟ್ ಗುಡ್ ಆರ್ ಬ್ಯಾಡ್? ಓಕೆ, ಗುಡ್. ಬ್ಯಾಡ್ ಬರಂಗಿಲ್ಲ ಇದ್ರಾಗ. Is the artist good? Call that one as x1. Call that one as x1. Because binary input. Suppose x1 is 1, artist is good. Suppose artist is not good, x1 is 0. Okay, good. Next. Second one. Is the weather good? ಅಂದರೆ ವಾತಾವರಣ ಚಲೋ ಐತಾ ಇಲ್ಲ? ಒಂದು ಮ್ಯೂಸಿಕಲ್ ಶೋ ಐತಂದರೆ ಒಂದು ದೊಡ್ಡ ಅಟ್ಮಾಸ್ಫಿಯರ್ನ ಎಲ್ಲ ಮಾಡ್ತಾರೆ, ಸ್ಟೇಜ್ ಶೋ ಅವೆಲ್ಲ ಇರ್ತಾವ. ಮಳೆ ಗಿಳೆ ಬಂತಂದ್ರೆ ಹೆಂಗ ಏನು ಕತೆ? ಓಕೆ, ಸಪೋಸ್ ವೆದರ್ ಈಸ್ ಗುಡ್ ಅಂದರೆ x2 ಈಸ್ ಕಾಲ್ಡ್ ಎಸ್ ಎ ವೆದರ್. x2 ಈಕ್ವಲ್ಸ್ ಟು 1 ಅಂದ್ರೆ ಏನರ್ಥ? ವೆದರ್ ಈಸ್ ಗುಡ್. x2 0 ಅಂದ್ರೇನು? ವೆದರ್ ಈಸ್ ನಾಟ್ ಗುಡ್. ಓಕೆ, ಗುಡ್. ಸೊ ನೆಕ್ಸ್ಟ್, ವಿಲ್ ದ ಫ್ರೆಂಡ್ ಕಮ್? ಒಂದು ಮ್ಯೂಸಿಕಲ್ ಶೋ ಹೋಗ್ಬೇಕಂದ್ರೆ ಮಾನಸಿಕ ಒಬ್ಬನ ಕುಂದ್ರಾಗ ಬರೋಂಗಿಲ್ಲ, ನಮ್ಮ ಸ್ವಲ್ಪ ಡ್ಯಾನ್ಸ್ ಹಾಕಕ್ಕೆ ಇನ್ನೊಬ್ರು ಬೇಕು ಬಗಲಿಗೆ. ಹೌದಾ? ಈಸ್ ದ ಫ್ರೆಂಡ್ ಕಮ್? ಅವ್ನು ಬಂದರೆ ಜಾಸ್ತಿ ಚೀರ್ ಇರ್ತದೆ, ಇಲ್ಲಾಂದ್ರೆ ಕಷ್ಟ. ನಾವು x3 ಈಸ್ ಕಾಲ್ಡ್ ಎ ಫ್ರೆಂಡ್ ಅಕಂಪನಿ. x3 ಈಸ್ 1 ಅಂದ್ರೆ ಅರ್ಥೇನು? ಫ್ರೆಂಡ್ ಬರ್ತಾ ಇದ್ದೇನೆ. x3 0 ಅಂದ್ರೇನು? ಫ್ರೆಂಡ್ ಬರ್ತಾ ಇಲ್ಲ. ಓಕೆ, ಗುಡ್. ಸೊ ನೆಕ್ಸ್ಟ್, ಈಸ್ ಫುಡ್ ಸರ್ವ್ಡ್? ಅಲ್ಲಿ ಊಟ ಕೊಡ್ತಾರಾ ಇಲ್ಲ? x4 ಈಸ್ ಸ್ಟ್ಯಾಂಡ್ಸ್ ಫಾರ್ ದ ಈಸ್ ದ ಫುಡ್ ಸರ್ವ್ಡ್. ಸಪೋಸ್ x4 ಈಸ್ 1 ಅಂದ್ರೆ ಅರ್ಥೇನು? ಫುಡ್ ಸರ್ವ್ ಮಾಡ್ತಾ ಇದ್ದಾರಾ? x4 ಈಸ್ 0, ಫುಡ್ ಸರ್ವ್ ಮಾಡ್ತಾ ಇಲ್ಲ. ನೆಕ್ಸ್ಟ್, ಈಸ್ ದ ಎಂಟ್ರಿ ಫ್ರೀ? ಎಂಟ್ರಿ ಫ್ರೀ ಐತಾ ಇಲ್ಲ? ಸಪೋಸ್ x4 ಈಸ್ x5, ಇಟ್ ಈಸ್ ಇಮ್ಮಿಟರಲ್, x2 ಆರ್ x3 ಸಮ್. ಇಟ್ಸ್ ಎ ವೇರಿಯಬಲ್, ಬೈನರಿ ವೇರಿಯಬಲ್. x4 ಈಸ್ x5, ಓಕೆ, x5 x5 ಈಕ್ವಲ್ಸ್ ಟು 1 ಅಂದ್ರೆ ಏನರ್ಥ? ಎಂಟ್ರಿ ಈಸ್ ಫ್ರೀ. x5 is 0 ಅಂದ್ರೆ ಅರ್ಥೇನು? ಎಂಟ್ರಿ ಈಸ್ ನಾಟ್ ಫ್ರೀ, ಅಂದರೆ ಸಮ್ ಕಾಸ್ಟ್ ಇರ್ತದೆ. ಓಕೆ, ದೀಸ್ ಆರ್ ಆಲ್ ದ ನೆಕ್ಸ್ಟ್ ವಾಟ್ ವೇಟ್ ಶುಡ್ ದೀಸ್ ಫ್ಯಾಕ್ಟ್ಸ್ ಹ್ಯಾವ್? ಅರ್ಥ ಆಯ್ತಾ? ಎಷ್ಟು ವೇರಿಯಬಲ್ಸ್ ಅದಾವಿಲ್ಲಿ? 5 ಅದಾವ. 5 ಬೈನರಿ ವೇರಿಯಬಲ್ಸ್. ಈಚ್ ಒನ್ ಆಫ್ ದಮ್ ಈಸ್ ಐದರ್ 1 ಆರ್ 0. ಆ 5 ವೇರಿಯಬಲ್ಸ್ಗೆ 5 ವೇಟ್ಸ್ ಕೊಡ್ತಾನೆ. ಆ ವೇರಿಯಬಲ್ಸ್ಗೆ 5 ವೇಟ್ಸ್ WH. ಆ ವೇಟ್ಸ್ ಯಾರಿಗೆ ಬಿಟ್ಟಿದ್ದು? ಇಂಡಿವಿಜುವಲ್, ನನಗೆ ಸಂಬಂಧಪಟ್ಟಿದ್ದಲ್ಲ, ನಿಮಗೆ ಸಂಬಂಧಪಟ್ಟಿದ್ದು. ಅಕಸ್ಮಾತ್ ನಾನು ಮ್ಯೂಸಿಕಲ್ ಶೋ ಹೋಗಲೇಬೇಕು ಅಂದರೆ 5 ಪ್ಯಾರಾಮೀಟರ್ನಾಗ, ಈ 5 ಪ್ಯಾರಾಮೀಟರ್ನಾಗ ಯಾವುದಕ್ಕೆ ವೆಯ್ಟ್ ಜಾಸ್ತಿ ಕೊಡ್ತಾರೆ ಅಂದರೆ ನಿಮಗೆ ಬಿಟ್ಟಿದ್ದದು. ಓಕೆ, ಸೊ ನಾವು ಓಕೆ ವೇಟ್ಸ್ ಕೊಟ್ಟಿವಿ. ನೆಕ್ಸ್ಟ್ ಏನು? ವೇಟ್ಸ್ ಕೊಟ್ಟ ತಕ್ಷಣ ಫ್ರಾಂಕ್ ರಸನ್ಬ್ಲಾಟ್ ಸಜೆಸ್ಟೆಡ್ ದ ಫಾಲೋಯಿಂಗ್ ಆಲ್ಗರಿದಮ್. ವಾಟ್ ಇಸ್ ದಟ್ ಒನ್? ಸೆಟ್ ಎ ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ. ಸೆಟ್ ಎ ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ ಒಂದು ಸೆಟ್ ವ್ಯಾಲ್ಯೂ ನೀವೇ ವಿಚಾರ ಮಾಡ್ಬೇಕು ಯಾವುದಂತೇಳಿ. ಓಕೆ, ಗುಡ್. ನೆಕ್ಸ್ಟ್, ಮಲ್ಟಿಪ್ಲೈ ಆಲ್ ಇನ್ಪುಟ್ಸ್ ವಿತ್ ದೈರ್ ವೇಟ್ಸ್. ವಾಟ್ ಇಸ್ ದ ಇನ್ಪುಟ್? x1 ಇಂಟು w1. x2 into W2, x3 into W3, x4 into W4, x5 into W5. Now weight and inputs multiply ಮಾಡ್ರಿ ಔಟ್ರನ್ನೆಲ್ಲ ಆ್ಯಡ್ ಮಾಡಿರಿ. ಓಕೆ. ಸೊ sum all the results. Sum ಅಂದರೆ W1 into x1 plus W2 into x2 plus W3 into x3 plus W4 into x4 plus W5 into x5 ಆ್ಯಡ್ ಮಾಡಿವಿ. Now activate the output. Activate the output. Suppose all the weighted sum idrinta W1 into x1, if it is exceeding the threshold, I am attending the musical show. If does not exceeding the threshold, I am not attending the musical show. This is the output. Okay. So now, okay, sorry. This is the criteria. R test is good. X1 is 0 or 1. Weather is good. X2 is 0 or 1. So these are all the criteria parameters, and these are all the input possible and weights. What is the W1? 0.7. This is not limited to 0.7. You can give your own weight. Okay, good. W2 is 0.6, W3 is 0.5, W4 is 0.3, W5 is 0.4. These are all the weights of my choice. These are the weights of my choice. You can have your own weights. Okay, good. So what is the next step? ಹೇಳ್ತೀರಿ? What is the next step? x1 0.0 or 1 into 0.1 like that. So this is the threshold value. Threshold value I am putting as 1.5. It's my own choice. You can have your own choice of threshold. Okay. Try to understand. Okay, that's all. Multiply all inputs with their weights. W1 into x1. So x1 into W1. 1 into 0.7. x1 ಎಷ್ಟು ತೊಗೊಂಡಿನಿ ಇಲ್ಲಿ? 1 ತೊಗೊಂಡಿನಿ. ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ವಾಟ್ ಇಸ್ ದ ಮೀನಿಂಗ್ ಆಫ್ ದಿಸ್ ಒನ್? ಆರ್ಟಿಸ್ಟ್ ಈಸ್ ಗುಡ್. ಆರ್ಟಿಸ್ಟ್ ಈಸ್ ಗುಡ್ ಅಂದರೆ ಮ್ಯೂಸಿಕಲ್ಸು ಕಂಪೋಸ್ ಮಾಡೋನು ಭಾಳ ಫೈನ್ ಇದಾನ. ದಟ್ಸ್ ವೈ 1. ಓಕೆ, ಗುಡ್. ಅಂಡ್ ವೆಯ್ಟ್ 0.7. x2 ಇಂಟು W2 0 ಇಂಟು 0.6. x2 ಎಷ್ಟು ತೊಗೊಂಡಿನಿ ಇಲ್ಲಿ? 0. ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ವೆದರ್ ಈಸ್ ನಾಟ್ ಗುಡ್. ವೆದರ್ ಈಸ್ ನಾಟ್ ಗುಡ್. Okay, this is one possible. That's all. Next, x3 into W3 1 into 0.5. x3 1 ತೊಗೊಂಡಿನ ಅದರ ಅರ್ಥ ಏನು? ಫ್ರೆಂಡ್ ಈಸ್ ಅಕಂಪನಿಂಗ್ ಯು. ಫ್ರೆಂಡ್ ಈಸ್ ನಿನ್ನ ಜೊತೆಗೆ ನಿಮ್ಮ ಫ್ರೆಂಡ್ ಬರ್ತಾ ಇದ್ದಾನೆ. ಓಕೆ, ಅದಕ್ಕೆ ವೆದರ್ ಬಗ್ಗೆ ತಲೆ ಕೆಡಿಸ್ಕೊಂಡಿಲ್ಲ ನೀನು. ನೆಕ್ಸ್ಟ್, x4 into W4. x4 ಎಷ್ಟು ತೊಗೊಂಡಿನಿ? 0. ಅಂದರೆ ಇದರ ಅರ್ಥ ಏನು? ಫುಡ್ ಈಸ್ ನಾಟ್ ಸರ್ವ್ಡ್. ಫುಡ್ ಈಸ್ ನಾಟ್ ಸರ್ವ್ಡ್. ಓಕೆ. ನೆಕ್ಸ್ಟ್, ಸಾರಿ, x5 into W5 1 into x5 1 ಅಂದ್ರೆ ಅರ್ಥ ಏನು? ಎಂಟ್ರಿ ಈಸ್ ಫ್ರೀ. ಎಂಟ್ರಿ ಈಸ್ ಫ್ರೀ. ಓಕೆ. ಸೊ ನಾವು ನೆಕ್ಸ್ಟ್ ಸಮ್ ಆಲ್ ದ ರಿಸಲ್ಟ್ಸ್ ಅಂದ್ರೇನು? ಸಮ್ ಆಲ್ ದ ರಿಸಲ್ಟ್ಸ್ ಅಂದ್ರೇನು? ವಾಟ್ ಈಸ್ x1 into W1 0.7, x2 into W2 0, x3 into W3 0.5, x4 into W4 0, x5 into W5 0.5. You add all the weighted sum. What is the weighted sum? ಏನು ಬಂದಿಲ್ಲಿ? 1.6. ಏನು ಬಂತು? 1.6. What is your threshold? 1.5. This weighted sum is 1.6. What is your threshold? 1.5. 1.6 is greater than the threshold or not? ಅಂತ ಅದರ ಅರ್ಥ ಏನು? ನಾನು ಮ್ಯೂಸಿಕಲ್ ಶೋ ಹೋಗ್ತಾ ಇದ್ದೀನ ಇಲ್ಲ? ಎಸ್, ಹೋಗ್ತಾ ಇದ್ದೀನಿ. ಅರ್ಥ ಆಯ್ತಲ್ಲ? ಸಪೋಸ್ ದಿಸ್ weighted sum ಸ್ಮಾಲರ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್ ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ನಾನು ಹೋಗ್ತಾ ಇಲ್ಲ ಅಂದರೆ ನಾನು ಏನು ವೇರಿಯಬಲ್ಸ್ ಕೊಟ್ಟಿರಲ್ಲ ವೆಯ್ಟ್ಸ್, ಆ ವೇಟ್ ಅಂದರೆ ಅಷ್ಟೇನು ಇಂಪಾರ್ಟೆಂಟ್ ಇಲ್ಲ ಅಂತ ಅರ್ಥ. ಓಕೆ, ಗುಡ್. ಸೊ ನಾವು ಇಂಟರ್ಪ್ರಿಟೇಷನ್ ಇನ್ನೊಂದು ನೆಕ್ಸ್ಟ್ ಹೇಳ್ತೀನಿ ನೋಡ್ರಿ. ಇಫ್ ದ ವೆದರ್ ಈಸ್ 0.6 ಫಾರ್ ಯು, ಸಾರಿ ಇನ್ನೊಂದು ಜಂಪ್ ಆಗಿದಂಗೈತೆ. ಇಫ್ ದ ವೆದರ್ ಈಸ್ 0.6 ಫಾರ್ ಯು, ಇಟ್ ಮೈಟ್ ಬಿ ಡಿಫ್ರೆಂಟ್ ಫಾರ್ ಸಮ್ ಒನ್ ಎಲ್ಸ್. ನನಗೆ 0.6 ತೊಗೊಂಡಿನಿ, ಬೇರೆ ಪರ್ಸನ್ ಬೇಕಾದ ತಗೋಬೋದು. ನಾನು 0.6 ತೊಗೊಂಡು ನೀವು ಅಷ್ಟೇ ತಗೋಬೇಕಂತೇನಿಲ್ಲ. ಓಕೆ. ಈ ಹೈಯರ್ ವೆಯ್ಟ್ಸ್ ಮೀನ್ಸ್ ಅಂದ್ರೆ ವೆಯ್ಟ್ ಜಾಸ್ತಿ ಇತ್ತಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ವೆಯ್ಟ್ ಜಾಸ್ತಿ ಇತ್ತಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ಅಂದ್ರೆ ಅರ್ಥ ಏನು? ಯು ಆರ್ ಗಿವಿಂಗ್ ಮೋರ್ ಇಂಪಾರ್ಟೆನ್ಸ್ ಟು ದಟ್ ವೇರಿಯಬಲ್. ಯು ಆರ್ ಗಿವಿಂಗ್ ಮೋರ್ ಇಂಪಾರ್ಟೆಂಟ್ ಟು ದಟ್ ವೇರಿಯಬಲ್. ಓಕೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ಇದ್ರಾಗ ಯಾವ ವೇರಿಯಬಲ್ಗೆ ಜಾಸ್ತಿ ವೆಯ್ಟ್ ಕೊಟ್ಟಿನಿ ನಾನು? ಫಸ್ಟ್ ಪ್ರಿಫರೆನ್ಸ್ ಯಾರಿಗೆ ಕೊಟ್ಟಿನಿ? ಆರ್ಟಿಸ್ಟಿಗೆ ಕೊಟ್ಟಿನಿ. ಲೀಸ್ಟ್ ಪ್ರಿಫರೆನ್ಸ್ ಯಾರಿಗೆ ಕೊಟ್ಟಿನಿ? ಯಾವುದು? ಫುಡ್. ಅಂದರೆ ನನ್ನ ವೆಯ್ಟ್ಸ್ ಮೇಲೆ ನಾನು ಡಿಸೈಡ್ ಮಾಡ್ಬೋದು. ನೀನು ಏನಂತೇಳಿ, ಈಸ್ ಗಿವಿಂಗ್ ಮೋರ್ ಇಂಪಾರ್ಟೆಂಟ್ ಟು ಆರ್ಟಿಸ್ಟ್ ಆ್ಯಂಡ್ ಲೀಸ್ಟ್ ಇಂಪಾರ್ಟೆಂಟ್ ಟು ಫುಡ್. ಅರ್ಥ ಆಯ್ತಾ? ಮಾಡ್ರೇಟ್ ಬಿಟ್ವೀನ್ ದೋಸ್. ಮಾಡ್ರೇಟ್ ಅಂದ್ರೇನು? 0.7 0.3 ನಡುವೆ ಬರೋ ವ್ಯಾಲ್ಯೂಸ್ಗೆ ಮಾಡ್ರೇಟ್ ಅಂತೀನಿ. ಓಕೆ, ಗುಡ್. So a higher weight means that the weather is more important to them. Okay. Next, if the threshold value is 1.5 for you, it might be different for someone else. ಇನ್ನೊಬ್ಬರಿಗೆ ಇನ್ನೊಬ್ಬರ ವ್ಯಾಲ್ಯೂ ಡಿಫ್ರೆಂಟ್ ಇರ್ಬೋದು. ನೆಕ್ಸ್ಟ್, ಎ ಲೋಯರ್ ಥ್ರೆಶೋಲ್ಡ್ ಮೀನ್ಸ್ ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ ಭಾಳ ಕಡಿಮೆ ಐತಂದರೆ ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ ಕಡಿಮೆ ಐತಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ನೀನು ಹೆಂಗೆ ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ ಕಡಿಮೆ ಇಟ್ಟು ಅಂದರೆ ಅವು ಏನೇ ಇರಲಿ ನೀನು ಮ್ಯೂಸಿಕಲ್ ಕನ್ಸರ್ಟ್ ಹೋಗ್ತದೆ ಅಂತ ಅರ್ಥ. ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ ಕಡಿಮೆ ಇಟ್ಟು ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? ನೀನು ಆಲ್ರೆಡಿ ಯು ಹ್ಯಾವ್ ಟೇಕನ್ ಡಿಸಿಷನ್, ವಾಟ್ ಎವರ್ ಮೇ ಬಿ ದ ಪ್ಯಾರಾಮೀಟರ್ಸ್, ಐ ಆಮ್ ರೆಡಿ ಟು ಗೋ ಅಂದರೆ ಅದರತ್ತೇನು? ಥ್ರೆಶೋಲ್ಡ್ ವ್ಯಾಲ್ಯೂ ಕಡಿಮೆ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ನಾನು ಧಾರವಾಡಕ್ಕೆ ಕಾನ್ಫರೆನ್ಸ್ಗೆ ಬರ್ತಾ ಇದ್ದೀನಿ ಅಂದರೆ ವಾಟ್ ಆರ್ ದ ಪ್ಯಾರಾಮೀಟರ್ಸ್? ಐ ವಾಂಟ್ ಟು ಮೀಟ್ ಡಾಕ್ಟರ್ ಶಿರಾಳ್ ಶೆಟ್ಟಿ, X1. ಐ ವಾಂಟ್ ಟು ಮೀಟ್ ಮೈ ಗೈಡ್ ಪ್ರೊಫೆಸರ್ ಬುಜುರ್ಕೆ, X2. ಐ ವಾಂಟ್ ಟು ನೆಕ್ಸ್ಟ್ ಇಂಟ್ರ್ಯಾಕ್ಟ್ ವಿತ್ ಆಲ್ ಮೈ ಸ್ಟೂಡೆಂಟ್ಸ್ ಅಂದರೆ ನನಗೆ ನೀವೇ ಕಲಿಬೇಕಂತೇನು, ಶಿರಾಳ್ ಸರ್ ಸ್ಟೂಡೆಂಟ್ಸ್ ಅಂದ್ರೂ ನಮ್ಮ ಸ್ಟೂಡೆಂಟ್ಸ್, ದಿಸ್ ಆರ್ ಆಲ್ ದ. ಬಟ್ ನಾನು ಬರಲೇಬೇಕಂತ ಇದ್ದೀನಿ ಇಲ್ಲಿ. ಐ ಆಮ್ ಗಿವಿಂಗ್ ಲೀಸ್ಟ್ ಇಂಪಾರ್ಟೆಂಟ್ ಟು ವೆಯ್ಟ್ಸ್. ಅರ್ಥ ಆಯ್ತಾ? ಓಕೆ, ಗುಡ್. ಸೊ ಇದೆಲ್ಲ ನಮ್ಮ ನ್ಯೂರಾನ್ನ ನಡೀತಾ ಇರ್ತೈತೆ, ನಮ್ಮ ತಲೆನ ನಡೀತಾ ಇರೋದ್ರ ನಾವು ಇಮಿಟೇಟ್ ಮಾಡ್ತಾ ಇದ್ವಿ, ಮಿಮಿಕ್ ಮಾಡ್ತಾ ಇದ್ವಿ. ಓಕೆ, ಗುಡ್. ನೆಕ್ಸ್ಟ್, ವಾಟ್ ಈಸ್ ದ ಪ್ರಾಬ್ಲಮ್ ಹಿಯರ್? ನ್ಯೂರಾನ್ ನಾವು ಇನ್ಪುಟ್ ಔಟ್ಪುಟ್ ಏನಿದ್ವು ಹೇಳ್ರಿ? ವಾಟ್ ಆರ್ ದ ಇನ್ಪುಟ್ ಬೈನರಿ. ಇನ್ಪುಟ್ ಔಟ್ಪುಟ್ ಏನು? ಬೈನರಿ. ವಿ ವಾಂಟ್ ಟು ಓವರ್ಕಮ್ ದಟ್ ಒನ್. ಅಂದರೆ ಇನ್ಪುಟ್ಸ್ ಯಾವಾಗಲೂ ಬೈನರಿ ಇರ್ಬೇಕಂತ ಏನಿಲ್ಲ. ಫಾರ್ ಎಕ್ಸಾಂಪಲ್, ವೆದರ್ ಈಸ್ ಗುಡ್ ಆರ್ ಬ್ಯಾಡ್ ಇನ್ ಧಾರವಾಡ? ವೆದರ್ ಈಸ್ ಗುಡ್ ಆರ್ ಬ್ಯಾಡ್? 1-0 ಅಂತಿಲ್ಲ. ಓಕೆ, 0.8. ಎದಕ್ಕಂತಂದರೆ ಮಳೆ ಬಂದರೆ ಒಂದು ಅರ್ಧ ತಾಸು ಬರುತ್ತೆ ಮತ್ತು ಫ್ರೀ ಕೊಡುತ್ತೆ. ಯಾವಾಗಲೂ ಬೆಳಿಗ್ಗಿನ ಸಂಜೆ ಮಟ್ಟ ಕಂಟಿನ್ಯೂಸ್ ಇರುತ್ತೆ. ಈ ಸೀಸನ್ ಸಾಧ್ಯನಿಲ್ಲ. ಸೊ 1 ಕೊಡೋದು ಸಾಧ್ಯ ಇಲ್ಲ, 0 ಕೊಡೋಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. ಐ ವಾಂಟ್ ಟು ಗಿವ್ 0.8. ಅದು ಇನ್ಪುಟ್ ಏನಾಯ್ತದು? ಬೈನರಿನಾ? ನೋ. ಇಟ್ ಲೈಸ್ ಬಿಟ್ವೀನ್ 0. ಇಟ್ ಮೇ ಎಕ್ಸೀಡ್ 1 ಆಲ್ಸೋ, ಜಸ್ಟ್ ರಿಯಲ್ ನಂಬರ್. ಓಕೆ, ಸೊ ಅದಕ್ಕೆ ಹಿ ಹ್ಯಾಸ್ ಒನ್ ಮೋರ್ ಆಲ್ಗರಿದಮ್ ಕಾಲ್ಡ್ ದಿಸ್ MP ನ್ಯೂರಾನ್. MP ಅಂದರೆ ಇಟ್ಸ್ ಎ ಕಾಂಟ್ರಿಬ್ಯೂಟರ್ ಫ್ರಮ್ 2 persons. Warren McCulloch, M stands from this one, and Walter Pitts. Whereas perceptron was introduced in he is introduced in 1957. Okay, MP neuron model accepts binary inputs and produces a binary output based on the certain threshold value which can be adjusted. This can be mainly used for classification problems. So there are classification problems ಅಂತೇಳಿ ಸೂಪರ್ವೈಸ್ಡ್ ಅನ್ಸೂಪರ್ವೈಸ್ಡ್ ಲರ್ನಿಂಗ್ ಅಂತ ಕಂಪ್ಯೂಟರ್ ಸೈನ್ಸ್ ಭಾಳ ವರ್ಕ್ ಮಾಡ್ತೀವಿ. ಯು ಕ್ಯಾನ್ ಕ್ಲಾಸಿಫೈ ಇಟ್, ನೋ ಪ್ರಾಬ್ಲಮ್, ವೆರಿ ಸಿಂಪಲ್. ಸೊ ಹೌ ಟು ಕ್ಲಾಸಿಫೈ ಸ್ಟೂಡೆಂಟ್ಸ್ ಇನ್ ದ ಕ್ಲಾಸ್ ರೂಮ್? ಒಂದು ಸೈಡ್ ಆ ಕಡೆ ಕೊಡ್ತೀರಿ, ಇಬ್ಬರು ಹೆಂಗೆ ಕೊಡ್ತಾರೆ ಯೂಶ್ವಲಿ? ಒಂದು ಕಡೆ ಲೇಡೀಸ್ ಕೊಡ್ತಾರೆ, ಇನ್ನೊಂದು ಕಡೆ ಜಸ್ಟ್ ಕ್ಲಾಸಿಫಿಕೇಶನ್. ಓಕೆ, ಸಪ್ರೇಟ್ ಮಾಡೋದನ್ನು. ಓಕೆ, ಗುಡ್. ಸೊ ನಾವು ಲಾಜಿಕಲ್ ಆ್ಯಂಡ್ ಗೇಟ್. ಸೊ ನಾವು ಒಂದು ವಿತೌಟ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಒಂದು ಮ್ಯೂಸಿಕಲ್ ಶೋಗೆ ಹೆಂಗೆ ನಮ್ಮ ಮೈಂಡ್ ಹೆಂಗೆ ವರ್ಕ್ ಆಗ್ತದೆ ನ್ಯೂರನ್ಸ್ ಮೇಲೆ ಅಂತ ನಾನು ತಿಳಿಸಿದೆ. ನಾವು ಇಟ್ ಈಸ್ ಶಿಫ್ಟ್, ನಾವು ಗೋಲ್ ಏನು, ವಾಟ್ ಈಸ್ ದ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್ ಬಿಹೈಂಡ್ ಅವರ್ ವರ್ಕ್. ಓಕೆ, ಅದರ ನಾವು ಗೋಲ್ ಬರ್ಬೇಕಂದ್ರೆ ವಾಟ್ ಇಸ್ ದ ಬೆಸ್ಟ್ ವೇ ಟು ಶಿಫ್ಟ್ ಫ್ರಮ್ ಯೂಶುವಲ್ ಎಕ್ಸ್ಪೀರಿಯನ್ಸ್ ಟು ಎ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ವಯಾ ಲಾಜಿಕಲ್ ಗೇಟ್. ಸೊ ವಾಟ್ ಇಸ್ ದ ಲಾಜಿಕಲ್ ಗೇಟ್? ಲಾಜಿಕಲ್ ಗೇಟ್ಸ್ ಏನೇನು ಕಲ್ತೀರಿ ನೀವು? AND gate, OR gate, NAND gate, NOR gate, JOR gate, number of it. So I have considered a simple gate, AND gate. How it works? I am taking only 2 inputs. How many inputs? 2 inputs. When it is both inputs are 1, output is 1. If one of the input is 0, what is the output? 0. So now, okay, good. Here x1, x2, 1 are 0. W1, W2 and bias is nothing but threshold. And output. So f of x is called activation function. What it will do? Activate means no activation andre 0. Activation andre 1. Andre ee kelsa maadu anta ಫೈರ್ ಅಂತಾರೆ. ಅದ್ರ ಏನಂತಾರೆ? ಫೈರ್. ನಿಮ್ಮ ನ್ಯೂರಾನ್ ಫೈರ್ ಆಗ್ತದೆ ಅಂದ್ರೆ ಅರ್ಥೇನು? ನ್ಯೂರಾನ್ ಫೈರ್ ಆಗ್ತದೆ, ಆ ಕೆಲಸ ಮಾಡ್ಬೇಕು ನೀವು. ನ್ಯೂರಾನ್ ಫೈರ್ ಆಗಿಲ್ಲ ಅಂದರೆ ಆ ಕೆಲಸ ಇಲ್ಲ ಅಂತ ಅರ್ಥ. ಸೊ ದಟ್ ಈಸ್ ಡನ್. ಇಫ್ ಎಫ್ ಆಫ್ ಎಕ್ಸ್ ಈಸ್ ಕಾಲ್ಡ್ ದ ಥ್ರೆಶೋಲ್ಡ್, ಎಕ್ಸ್ ಈಸ್ ಲೆಸ್ ದ್ಯಾನ್ ಆರ್ ಈಕ್ವಲ್ಸ್ ಟು 0, 0. ವೆನ್ ಎವರ್ ಎಕ್ಸ್ ಈಸ್ ಗ್ರೇಟರ್ ದ್ಯಾನ್ ಈಕ್ವಲ್ಸ್ ಟು 0, 1. ಹೆಂಗಾದ್ರೆ ಶಿಫ್ಟ್ 0 ಆ ಕಡೆಗೆ ಶಿಫ್ಟ್ ಮಾಡಿ ಈ ಕಡೆ ಇಟ್ಸ್ ಜಸ್ಟ್ ಲೈಕ್ mod x. ಓಕೆ, ಗುಡ್. ನ್ಯೂರಲ್ ರೆಪ್ರೆಸೆಂಟೇಷನ್ ಆಫ್ ಆ್ಯಂಡ್ ಗೇಟ್. ಓಕೆ, ನಾವು ಇದ್ರಾಗ ಅನ್ನೋನ್ಸ್ ಯಾವ ಹೇಳ್ತೀರಿ? ಇದ್ರಾಗ ಅನ್ನೋನ್ಸ್ ಏನು, ನೌನ್ಸ್ ಏನು, ಅನ್ನೋನ್ಸ್ ಏನು? ಆ್ಯಂಡ್ ಗೇಟ್ನಾಗ ಐ ನೋ x1 and x2, ಐ ನೋ ಔಟ್ಪುಟ್. ವಿಚ್ ಆರ್ ದ ಅನ್ನೋನ್ಸ್ ಇಯರ್? ವಿಚ್ ಆರ್ ದ ಅನ್ನೋನ್ಸ್? ವೆಯ್ಟ್ಸ್, W1, W2, ಥ್ರೆಶೋಲ್ಡ್. ಏನು ಹೇಳ್ರಿ? ಆ್ಯಂಡ್ ಗೇಟ್ನಾಗ, ಆ್ಯಂಡ್ ಗೇಟ್ ನ್ಯೂರಲ್ ನೆಟ್ವರ್ಕ್ ಮಿಮಿಕ್ ಮಾಡುತ್ತಂದ್ರೆ ವಿಚ್ ಆರ್ ದ ನೌನ್ ಕ್ವಾಂಟಿಟೀಸ್? ಇನ್ಪುಟ್ ಗೊತ್ತಿದೆ, ಔಟ್ಪುಟ್ ಗೊತ್ತಿದೆ. ಏನು ಗೊತ್ತಿದೆ? ಇನ್ಪುಟ್ ಗೊತ್ತಿದೆ, ಔಟ್ಪುಟ್ ಗೊತ್ತಿದೆ. ನನಗೆ ಗೊತ್ತಿಲ್ಲಾರ್ದೇನಿದ್ರಾಗ ವೆಯ್ಟ್ಸ್ ಆ್ಯಂಡ್ ಥ್ರೆಶೋಲ್ಡ್. ವೆಯ್ಟ್ಸ್ ಅಂದರೆ W1, W2, ಥ್ರೆಶೋಲ್ಡನ್ನ ಬಯಾಸ್ ಅಂತ ಕೂಡ ಕರಿತೀನಿ ನಾನು. ಅರ್ಥ ಆಯ್ತಾ ಇಲ್ಲ? ನಾವು ಬೇಸ್ಡ್ ಆನ್ ದಿಸ್ ಸಿಸ್ಟಮ್ ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಫೈಂಡ್ ವೆಯ್ಟ್ಸ್ W1, W2, ಥ್ರೆಶೋಲ್ಡ್ ವಿತೌಟ್ ಮಚ್ ಮ್ಯಾಥಮೆಟಿಕ್ಸ್. Without much mathematics. Okay, good. So now logical AND gate, x1 and x2 both are 1, output is 1, x1 conjunction x2. If one of them is 0, what is x1 conjunction x2? 0. ಹೌದಾ? ಎಷ್ಟು ರೋಸ್ ಅದಾವೆ ಇಲ್ಲಿ ನಮ್ಮಲ್ಲಿ? 4 ರೋಸ್ ಅದಾವೆ. ಓಕೆ, ಗುಡ್. ಪರ್ಸೆಪ್ಟ್ರನ್ ಆಲ್ಗಾರಿದಮ್ ಸ್ಟೇಟ್ಸ್ ದಟ್ ಪ್ರಿಡಿಕ್ಷನ್ ಅಂದರೆ x1 conjunction x2 ಏನಿರ್ಬೋದು? ಸೊ 0, W x plus B. What is W into x here? W1 into x1 plus W2 into x2. B is threshold. Okay. Next, W x plus B. W1 into x1 plus W2 into x2. If this is exceeds threshold. Okay, good. Is now have written W1 into x1 plus W2 into x2. ಏನಂತ ಕರೀತಾರೆ ಅದನ್ನ? Inner product of W and x. Inner product of W. What is W? W1, W2. What is x? X1, x2. It is inner product. Okay. Good. So learning parameters for AND gate. What are the unknowns? W1, W2, B. These are called parameters. And I am going to calculate. Calculate ಅಂದ್ರೇನು? ನಮ್ಮ ನ್ಯೂರಾನ್ ಕಲಿತಿದೆ. That's why called learning. ನಮ್ಮ ನ್ಯೂರಾನ್ ಕಲಿತಿದೆ ಅಂದರೆ ಅದ್ರ ಏನಾಯ್ತವ? ಲರ್ನಾನ್. ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ಫೈಂಡ್ ದ ವೇಟ್ಸ್ W1, W2 and B ಫಾರ್ ದ ಕರಸ್ಪಾಂಡಿಂಗ್ ಲಾಜಿಕಲ್ ಗೇಟ್. ಈ ವೇಟ್ಸ್ ಏನು ಪ್ಯಾರಾಮೀಟರ್ಸ್ ಅಂತೀವಿ, ಪ್ಯಾರಾಮೀಟರ್ಸ್ ಆಫ್ ದ ನೆಟ್ವರ್ಕ್. ಈ ವೇಟ್ಸ್ ನಾವು ಕಲಿಯೋದ್ರೆ ಏನಂತೀವಿ? ಲರ್ನಿಂಗ್ ಅಂತ ಅಷ್ಟೇ. ಓಕೆ, ನಾವು ವೆರಿ ಗುಡ್. ಸೊ ನಾವು ಲೆಟ್ W1, W2 ವೇಟ್ಸ್ ಆ್ಯಂಡ್ B ಬಯಾಸ್ ಥ್ರೆಶೋಲ್ಡ್ ಟು ಡಿಟರ್ಮೈನ್. ಸೊ ವಿತ್ ದ ಫಾಲೋಯಿಂಗ್ ಕಂಡೀಷನ್ಸ್. ವಾಟ್ ಆರ್ ದ ಫಾಲೋಯಿಂಗ್ ಕಂಡೀಷನ್ಸ್? W1 into 1 plus W into 1. ಎದಕ್ಕೆ 1 ತೋಣಿನಲ್ಲಿ? ಎದಕ್ಕೆ 1 ತೋಣಿನಿ? x1 is 1, x2 is 1. I supposed to calculate which one? W1, W2. I am using this data now. So now is greater than or equals to B. ಎದಕ್ಕೆ greater than or equals to B ತೋಣಿನಲ್ಲಿ? Both 1, 1 ಇದ್ದಾಗ what is the output? Greater than threshold or less than threshold? It must be greater than threshold because output is 1. That's why it exceeding B. What is B? Threshold. ಅರ್ಥ ಆಯ್ತಾ? ಗುಡ್. ನೆಕ್ಸ್ಟ್, W1 into 1 plus W into 0 less than B ಎದಕ್ಕೆ ತೊಗೊಂಡಿನಿ ಹೇಳ್ತೀರಿ? Because x1 is how much? 1. x2 is how much? 0. It is output ಇದು ಫೈರ್ ಆಗ್ಬೇಕಾ ನಾನ್ ಫೈರಿಂಗ್? ಔಟ್ಪುಟ್ ಇಸ್ 0 ಅಂದರೆ ಲೆಸ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್ ಇರ್ಬೇಕಾ ಗ್ರೇಟರ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್ ಇರ್ಬೇಕಾ? ಲೆಸ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್. ಓಕೆ, ಗುಡ್. ದಟ್ಸ್ ವೈ ಐ ಹ್ಯಾವ್ ಕನ್ಸಿಡರ್ W1 into 1 ಪ್ಲಸ್ W2 into 0 ಲೆಸ್ ದ್ಯಾನ್ B. ಸೊ ಸಿಂಪ್ಲಿಫೈ ಮಾಡಿದ್ರೆ ಏನು ಬರುತ್ತೆ ನಮಗೆ? W2 is smaller than B. ಸೊ ನೆಕ್ಸ್ಟ್ W1 into 0 ಪ್ಲಸ್ W2 into 0 is ಲೆಸ್ ದ್ಯಾನ್ B ಎದಕ್ಕೆ ತೊಗೊಂಡಿನಿ? W1, W2 ನಾನು ಕಂಡುಹಿಡಬೇಕು. x1 ಎಷ್ಟಿದೆ? 0. x2 ಎಷ್ಟಿದೆ? 0. ಇದು ಔಟ್ಪುಟ್ 0 ಇದೆ, 1 ಇದೆನಾ? ಬೋತ್ ಆರ್ 0. ವಾಟ್ ಈಸ್ ಯುವರ್ ಔಟ್ಪುಟ್? 0. ಅಂದರೆ ಲೆಸ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್ ಇರ್ಬೇಕಾ ಗ್ರೇಟರ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್ ಇರ್ಬೇಕಾ? ಎಸ್, ಲೆಸ್ ದ್ಯಾನ್ ಥ್ರೆಶೋಲ್ಡ್. ದಟ್ಸ್ ವೈ ಐ ಹ್ಯಾವ್ ಕನ್ಸಿಡರ್ ಲೆಸ್ ದ್ಯಾನ್ 0. ನೆಕ್ಸ್ಟ್, ಸೊ ದೀಸ್ ಆರ್ ಆಲ್ ದ 4 ಫಾರ್ ಎವ್ರಿ ಕಂಡೀಷನ್ 1 ಈಕ್ವೇಷನ್ ಬಂತು ನನಗೆ. ಎಷ್ಟು ರೋಸ್ ಅದಾವಲ್ಲಿ? 4 ರೋಸ್ ಅದಾವೆ. ಎಷ್ಟು ಈಕ್ವೇಷನ್ ಸಿಕ್ಕು ನನಗೆ? 4 ಈಕ್ವೇಷನ್ ಸಿಕ್ಸು. ವಾಟ್ ಆರ್ ದ ಅನ್ನೋನ್ಸ್? ಹೌ ಮೆನಿ ಅನ್ನೋನ್ಸ್? 3 unknowns. What are those? W1, W2, B. It is sufficient for me to find these values because I am having how many equations? 4. Okay, good. So from the row 4 ಏನು ಹೇಳುತ್ತೆ ನನಗೆ? B is positive. Threshold must be positive. Choice is yours. ನೀನು ಬೇಕಾದ ಪಾಸಿಟಿವ್ ನಂಬರ್ ತಗೋ, ನನಗೆ ಸಂಬಂಧ ಇಲ್ಲ. You take any B positive. 4th row suggest me to consider any B positive. Choice is yours. Next. Row 3 ಅಂದರೆ ರಿವರ್ಸ್ ಹೋಗ್ತಾ ಇದ್ದೀನಿ ನಾನು. Row 3 suggest me W2 ಅಂದರೆ ಇದು. W2 must be ಹೆಂಗಿರಬೇಕು? Smaller than B. I am giving positive number to you. How to give back to me a smaller number? You just multiply any number between 0 to 1. That going to number is going to be smaller than that one. So now, ಇಲ್ಲಿ ಎಷ್ಟು ತೊಗೊಂಡು ನಾನು 0.6 into B ತೊಗೊಂಡಿನಿ. Choice is yours. You can may consider 0.7 into B. It is immaterial. Next, third row I have utilized. Second row, what is the second row suggest me? W1 must be smaller than B. ಅಂದರೆ what is W1 I am considering? 0.5 into B. ಎದಕ್ಕೆ 0.6, 0.5 ತೊಗೊಂಡಿನಿ ನಾನು? ಎದಕ್ಕೆ 2.6 ತೊಗೊಂಡಿಲ್ಲ? ಅಥವಾ ವೈ ನಾಟ್ ಐ ಹ್ಯಾವ್ ಕನ್ಸಿಡರ್ 0.3? ಬಿಕಾಸ್ ನನಗೆ ರೋ 1 ಆಗಬೇಕು. ರೋ 1 ಹೆಂಗಿರಬೇಕು? W ಸಮ್ ಆಫ್ ದೀಸ್ ಟು ಮಸ್ಟ್ ಬಿ ಗ್ರೇಟರ್ ದ್ಯಾನ್ B ಇರಬೇಕು. ದಟ್ಸ್ ವೈ ಐ ಹ್ಯಾವ್ ಕನ್ಸಿಡರ್ಡ್ 0.6 and 0.5. W1 plus W2 0.6 into B plus 0.5 into B. This row 1 satisfied. ಅಕಸ್ಮಾತ್ ನಾನು 0.6, 0.3 ತೊಗೊಂಡಿದ್ರೆ ಏನಾಗ್ತಿತ್ತು? 0.6, 0.3 ತೊಗೊಂಡ್ರೆ ಏನಾಗ್ತಿತ್ತು? 0.9 into B ಆಗ್ತದೆ. Is it greater than B? No. Okay, good. So thus we have learned the required weights or not. Now suppose B equals to 2. Suppose B equals to 2. What is W1? What is W1? 0.6 into 2, how much? 0.6 into 2, how much? 1.2. Yes? Good. What is W2 is 1.2. What is W1? 0.5 into 2, how much? 1. We have learned all the weights and biases. These are the weights corresponding to AND gate. Now f of now this is what is AND gate function again? W1 into x1 plus W2 into x2 plus B. Okay, good. We have learned the weights and biases. We have learned the weights and threshold. We can do the same job if we are willing. Do for OR gate. Do for OR gate. ಅಂದರೆ ಏನು ಬರುತ್ತಲ್ಲಿ? ಎಷ್ಟು ರೋಸ್ ಅದಾವ? 4 ರೋ, 4 ಇಕ್ವೇಷನ್ ಬರುತ್ತೆ. We can try. And based on the 4 equations, you can easily compute weights and biases. Okay, good. Good. Now AND gate is over. Next ಏನು? Now you take if any function ಅಂದರೆ ಫಸ್ಟ್ಗೆ ಅನೌನ್ಸ್ ಮಾಡಿದ್ದಾನೆ. ಎನಿ ಫಂಕ್ಷನ್ ಮೀನ್ಸ್ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಆನ್ ಎ ಕಾಂಪ್ಯಾಕ್ಟ್ ಸೆಟ್. ಎನಿ ಫಂಕ್ಷನ್ ಮೀನ್ಸ್ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಆನ್ ಎ ಕಾಂಪ್ಯಾಕ್ಟ್ ಸೆಟ್. ಇದಕ್ಕಿಂತ ಮುಂಚೆ ನಿಮಗೆ ಡೆನ್ಸ್ ಅಂದರೆ ಗೊತ್ತಾಯ್ತಾ? ಹೇಳ್ರಿ ನಾನು. ಡೆನ್ಸ್ DENSC ಕೇಳಿರಲಿಲ್ಲ ಹೆಸರೆಲ್ಲಾದ್ರು? ಡೆನ್ಸ್ ಕೇಳಿಗಿಲ್ಲಮ್ಮ? ಹೇಳು. ಸೇ ಸರ್ ಇವರು ಸರ್ ಡೆನ್ಸ್ ಹೆಸರು ಕೇಳಿಗಿಲ್ಲ, ಆನ್ಸರ್ ಕೇಳಿಗಿಲ್ಲ. ಎಲ್ಲಿ ಕೇಳಿ? CBTನ ಮಾತಾಡ್ತಿದ್ರು ಒಂದಿಬ್ರು ಮೂರು. ಡೆನ್ಸ್ ಅಂದ್ರೆ ಹಿಂಗೆ ಹೆಂಗೆ ಅಂದಿಲ್ಲ ಹೇಳಮ್ಮ. ಕೇಳಿರೇ ಇಲ್ಲ. ಡೆನ್ಸ್ ಅಂದ್ರೆ ಏನು ಕೇಳಿದ್ರೆ ಭಾರಿ ಸಂತೋಷ. ಏನು ಆನ್ಸರ್ ಏನು? ಡೆನ್ಸ್ ಅಂದ್ರೆ ಏನು? ಯಾಕಂದ್ರೆ ಈ ಪಾಯಿಂಟ್ ಮೇಲೆ ನಾವು ಮಾತಾಡೋದು ನೆಕ್ಸ್ಟ್. ಹೇಳಪ್ಪ, ಡೆನ್ಸ್ ಅಂದ್ರೆ ಏನು ಹೇಳಿ ನೋಡೋಣ. ಗೊತ್ತಾಯ್ತಿಲ್ಲ ಡೆನ್ಸ್ ಅಂದ್ರೆ? ಗೊತ್ತಿಲ್ಲ? ಹೇಳ್ತಾ ನೋಡಿ, ಸಿಂಪಲ್. ನಾವು Marathi people are dense in Belgaum ಅಂದ್ರೆ ಅದರ ಅರ್ಥ ಏನು? Marathi people are dense in Belgaum. ನೋಡ್ರಿ, ನಾನು ಏನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ ಅಂದರೆ ಲೂಸ್ಲಿ ಸ್ಪೀಕಿಂಗಿಂದ ಫೈನರ್ ಬರ್ತೀನಿ. ಓಕೆ, Marathi people are dense in Belgaum ಅಂದ್ರೆ ಅರ್ಥ ಏನು? ನಿಮ್ಮ ಬೆಳಗಾಂ ಸಿಟಿನಲ್ಲಿ ಒಂದು 10-15 ಮಂದಿ ಇದ್ರಂತ ಕೊಟ್ಟರು. ಆ 10-15 ಮಂದಿನ ತೊಗೊಂಡ್ರೆ ಅದ್ರಾಗ ಒಬ್ಬರಾದರೂ ಮರಾಠಿ ಮಾತಾಡೋರು ಇರ್ತಾರ. ಅರ್ಥ ಆಯ್ತಾ ಇಲ್ಲ? ಓಕೆ, ಅದ್ರ ಡೆನ್ಸ್. ಸೆಟ್ ಆಫ್ ಆಲ್ ಫಿಶಸ್ ಆರ್ ಡೆನ್ಸ್ ಇನ್ ಡ್ಯಾಮ್. ಡ್ಯಾಮ್ ಅಂದ್ರೆ ಒಂದು ಟೊಪಾಲಜಿಕಲ್ ಸ್ಪೇಸ್. ಎಕ್ಸ್, ಕ್ಯಾಪಿಟಲ್ ಎಕ್ಸ್. ವಾಟ್ ಇಸ್ ಕ್ಯಾಪಿಟಲ್ ಎಕ್ಸ್? ಡ್ಯಾಮ್ ಇಸ್. ಡ್ಯಾಮ್ ಅಂದ್ರೆ ನೀರು ಇರ್ತದೆ, ಪೂರ್ ತುಂಬಿರ್ಬೇಕು ಮತ್ತೆ ಅದು. ಓಕೆ, ಒಂದು ದೊಡ್ಡ ಡ್ಯಾಮ್. ನಮ್ಮ ಈಜೆಲ್ಲ ಹೊಸಪೇಟೆ ಡ್ಯಾಮ್ ನಮ್ಗೆ ಭಾಳ ಹತ್ತಿರ ಇರ್ತದೆ ಅದು. ಹೊಸಪೇಟೆ ಡ್ಯಾಮ್, ನೀವು ಯಾವುದಾದ್ರು ಒಂದು ಡ್ಯಾಮ್ ತೊಗೊಡ್ರಿ, ನಾನು ಬೇಡ ನಂಗೆ. ಯು ನೇಮ್ ಇಟ್. ಕ್ಯಾಪಿಟಲ್ ಎಕ್ಸ್ ಈಸ್ ಅ ಹೊಸಪೇಟೆ ಡ್ಯಾಮ್. ನಾವು ಎ, ಕ್ಯಾಪಿಟಲ್ ಎ ಈಸ್ ಎ ಸಬ್ಸೆಟ್ ಆಫ್ ಎಕ್ಸ್. ಎ is the set of all fishes in dam. ಏನಿಡ್ರಿ? set of all fishes in dam A. Okay, ನಾವು ಮೀನು ಹೆಂಗೆ ಹಿಡಿತೀರಿ ನೀವು? ಯಾರಾದ್ರೂ ಹೇಳ್ತೀರಿ ಮೀನು ಹೆಂಗೆ ಹಿಡಿತೀರಮ್ಮ? ನೋಡಿರಲಿಲ್ಲ ಯಾರನ್ನ? ಬಲೆ ಹಿಡಿತಿರೋದಿಲ್ಲ. ನಾವು ದಸ್ ಈಸ್ ಎ ಓಪನ್ ಸೆಟ್, ಯುವರ್ ನೆಟ್ ಈಸ್ ಎ ಓಪನ್ ಸೆಟ್. ನಾವು ಒಂದು ಹಡಗು ತೊಗೊಂಡು ಮಿಡ್ ಡ್ಯಾಮ್ನಾಗ ಹೋಗು. ನಾವು ಯು ಥ್ರೋ ಎ ನೆಟ್, ಓಕೆ, ನೆಟ್ ಅದ್ರಾಗ ಏನು ಬಂದು ಬೀಳ್ತಾವ? ಸ್ವಲ್ಪ ತಾದ್ಮೇಲೆ ಏನು ಬಂದು ಬೀಳ್ತಾವ? ಮೀನು. ನಾವು ಯು ಕ್ಯಾನ್ ಅಂದ್ರೇನು? ಯು ಹ್ಯಾವ್ ಫೈಂಡ್ ಒನ್ ಫಿಶ್ ಇನ್ ದಟ್ ನೆಟ್, ಯು ಹ್ಯಾವ್ ಫೈಂಡ್ ಅಟ್ಲೀಸ್ಟ್ ಒನ್ ಫಿಶ್ ಇನ್ ದಟ್ ನೆಟ್. ಅಂದ್ರೆ ಅದ್ರ ಏನಂತಾರೆ? ಡೆನ್ಸ್ ಅಂತ. ಏನಂತಾರೆ ಅದನ್ನ? ಡೆನ್ಸ್. ಓಕೆ, ಸೊ ಸೆಟ್ ಆಫ್ ಆಲ್ ಫಿಶಸ್ ಆರ್ ಡೆನ್ಸ್ ಇನ್ ಡ್ಯಾಮ್. ವಾಟ್ ಆರ್ ದ ಓಪನ್ ಸೆಟ್ ಇಯರ್? ವಾಟ್ ಆರ್ ದ ಓಪನ್ ಸೆಟ್? ನೆಟ್. ಇಫ್ ಯು ಥ್ರೋ ಎ ಅಂದರೆ ಎವ್ರಿ ನಾನ್ ಎಂಟಿ ಓಪನ್. ಮತ್ತು ಈ ನಾನ್ ಎಂಟಿ ಅಂತ ಎದಕ್ಕಂತೀವಿ ನಾವು? ಅದು ಇಂಪಾರ್ಟೆಂಟ್. ಸಪೋಸ್ ಇಫ್ ಯು ಥ್ರೋ ಎ ನೆಟ್ ಪಂಕ್ಚರ್ಡ್ ಅಟ್ ಸಮ್ವೇರ್ ಎಲ್ಸ್, ಒಂದು ತೂತು ಭಾಳ ದೊಡ್ಡ ಬಿತ್ತಂದರೆ ಏನು ಮಾಡುತ್ತೆ? ಒಂದು ಕಡೆ ಬರ್ತದೆ, ಒಂದು ಕಡೆ ಓದುತ್ತೆ. ದಟ್ಸ್ ವೈ ಯು ಆರ್ ಕನ್ಸಿಡರಿಂಗ್ ಎಂಟಿ ಸೆಟ್, ನಾನ್ ಎಂಟಿ ಸೆಟ್? ನಾನ್ ಎಂಟಿ ಸೆಟ್. ಎ ನಾನ್ ಎಂಟಿ ಓಪನ್ ಸೆಟ್ ಕಂಟೈನ್ಸ್ ಅಟ್ ಲೀಸ್ಟ್ ಒನ್ ಪಾಯಿಂಟ್. ಅಂದರೆ ದಟ್ಸ್ ವೈ ಸೆಟ್ ಆಫ್ ಆಲ್ ರೇಷನಲ್ ನಂಬರ್ಸ್ ಆರ್ ಡೆನ್ಸ್ ಇನ್ ಆರ್. ಅಂದ್ರೆ ಅರ್ಥೇನು? ಸೆಟ್ ಆಫ್ ಆಲ್ ರೇಷನಲ್ ನಂಬರ್ಸ್ ಆರ್ ಡೆನ್ಸ್ ಇನ್ ಆರ್ ಅಂದ್ರೆ ಅರ್ಥೇನು? ಎಕ್ಸ್ ಈಸ್ ಆರ್, ಎ ಈಸ್ ಕ್ಯೂ, and what are the open sets? Open interval. In any open interval, you can find at least one rational number or not? Yes, very good. Now it is distance. Now I am taking any real number x. I can take any real number x, and you can pick, and correspondingly epsilon greater than 0. Choice is yours. Now I can find one rational number based on x and epsilon such that distance between x and rational number called small r. Distance ಅಂದ್ರೇನು? mod of x minus r is small. This is called, ಒಂದು ಓಪನ್ ಸೆಟ್ಸ್ನಾಗ ಹೇಳಿವಿ, ಒಂದು ಡಿಸ್ಟೆನ್ಸ್ನಾಗ. ಬೋತ್ ಆರ್ ಸೇಮ್, ಬೋತ್ ಆರ್. ಎದಕ್ಕಂದರೆ ಟೊಪಾಲಜಿಕಲ್ ಸ್ಪೇಸ್ನಾಗ ಡಿಸ್ಟೆನ್ಸ್ ಕಾನ್ಸೆಪ್ಟ್ ಗೊತ್ತಿಲ್ಲದ್ರು ನಡೀತೈತೆ, ಇಲ್ಲಿ ಟೊಪಾಲಜಿಕಲ್ ಸ್ಪೇಸ್ನಾಗ ಡಿಸ್ಟೆನ್ಸ್ ಕಾನ್ಸೆಪ್ಟ್ ಗೊತ್ತಿರ್ತೈತೆ ಅಷ್ಟೇ. ಓಕೆ, ಗುಡ್. ನಾವು ರೇಷನಲ್ ನಂಬರ್ ಈಸ್, ಓಕೆ, ನಾವು ರಿಯಲ್ ನಂಬರ್ಸ್ ಮತ್ತು ಎಪ್ಸಲನ್, ಇವು ಭಾಳ ಇಂಪಾರ್ಟೆಂಟ್. ನಾವು capital X is nothing but set of all continuous functions on a compact set. What is capital X? Set of all continuous functions on compact set. ಅರ್ಥ ಆಯ್ತಾ? ಇಲ್ಲ. This is dam. Dam is replaced what? Your dam is replaced by what? Set of all continuous functions on a compact set. Now capital A. What is capital A? Neural networks. Set of all neural networks. Epsilon same is as. ಓಕೆ, ನಿನ್ನ ಒಂದು ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಕೊಟ್ಟರೆ, ಒಂದು ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಜೊತೆಗೆ ಏನು ಕೊಡಬೇಕು? ಒಂದು ಎಪ್ಸಲಾನ್ ಕೊಡ್ಬೇಕು. ನನಗೆ ಏನು ಹೇಳ್ರಿ? ಒಂದು ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಜೊತೆ ಏನು ಕೊಡಬೇಕು? ಒಂದು ಎಪ್ಸಲಾನ್ ಕೊಟ್ಟರೆ ನಾನು ಐ ವಿಲ್ ಗಿವ್ ಇಟ್ ಟು ಎ ನ್ಯೂರಲ್ ನೆಟ್ವರ್ಕ್ ಟು ಯು ಸಚ್ ದಟ್ ಎಫ್ ಆಫ್ ಎಕ್ಸ್ ಈಸ್ ಎ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಆ್ಯಂಡ್ ಎಫ್ ಹ್ಯಾಟ್ ಆಫ್ ಎಕ್ಸ್ ಈಸ್ ಎ ನ್ಯೂರಲ್ ನೆಟ್ವರ್ಕ್ ಫಂಕ್ಷನ್. ಡಿಸ್ಟೆನ್ಸ್ ಬಿಟ್ವೀನ್ ದೆಮ್ ಈಸ್ ಸ್ಮಾಲ್ ವಾಟ್ ಎವರ್ ಮೇ ಬಿ ದ ಎಕ್ಸ್ ಓವರ್ ದ ಕಾಂಪ್ಯಾಕ್ಟ್ ಸೆಟ್. ಅರ್ಥ ಆಯ್ತಾ? ಇದೇ ಥಿಯರಮು ನೀವು ವಿರ್ಸ್ಟ್ರಾಸ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಥಿಯರಮ್ ಹೆಸರು ಕೇಳಿರಿಲ್ಲ? ವಿರ್ಸ್ಟ್ರಾಸ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಥಿಯರಮ್ ಹೆಸರು ಕೇಳಿರೇ ಇಲ್ಲ? ಕೇಳಿರ? ಯಾರಾದ್ರೊಬ್ಬರು ಸ್ಟೇಟ್ಮೆಂಟ್, ನೋ ಪ್ರಾಬ್ಲಮ್, ನಿಮ್ಗೆ ಯಾರನ್ನ ತಪ್ಪು ಮಾಡಿದ್ರು ನಾನು ನಿಮ್ಗೆ ಯಾರಿಗೂ ಹ್ಯಾಂಗ್ ಮಾಡೋಂಗಿಲ್ಲ ಹೇಳ್ರಿ, ನೋ ಪನಿಷ್ಮೆಂಟ್ ಟು ಯು. ತಪ್ಪು ಹೇಳಿದ್ರೂ ನಡೀತದೆ. ಪಾರ್ಟಿಸಿಪೇಷನ್ ಈಸ್ ಇಂಪಾರ್ಟೆಂಟ್. ಗಿವ್ ಮಿ ಎ ಸ್ಟೇಟ್ಮೆಂಟ್ ಆಫ್ ವಿರ್ಸ್ಟ್ರಾಸ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಥಿಯರಮ್. ಇಲ್ಲ, ಅದ್ರ ಮೇಲೆ ಡಿಪೆಂಡ್ ಇದೆ. ಏನಿಲ್ಲ, ಜಸ್ಟ್ ಐ ಆಮ್ ಗೋಯಿಂಗ್ ಟು ರಿಪ್ಲೇಸ್. ಡ್ಯಾಮ್ ಈಸ್ ರಿಪ್ಲೇಸ್ ಬೈ ಸೆಟ್ ಆಫ್ ಆಲ್ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ಸ್. ವಾಟ್ ಈಸ್ ಕ್ಯಾಪಿಟಲ್ ಎ? ಸೆಟ್ ಆಫ್ ಆಲ್ ಪಾಲಿನಾಮಿಯಲ್ಸ್. ವಾಟ್ ಈಸ್ ಕ್ಯಾಪಿಟಲ್ ಎ? ಸೆಟ್ ಆಫ್ ಆಲ್ ಪಾಲಿನಾಮಿಯಲ್ಸ್. Now give me a continuous function and epsilon. I will give back to a polynomial of degree based on that epsilon, such that distance between f of x and polynomial is small, and less than epsilon for every x belongs to the compact set. Now polynomials are replaced by networks. Next ಇನ್ನೊಂದು theorem ಬರ್ತದೆ. set of all piecewise constant functions are dense in set of all continuous functions on a compact set. ಅಂದ್ರೇನು? ಐ ಆಮ್ ನಾಟ್ ಪ್ರಿಕಿಂಗ್ ಎಕ್ಸಲೆಂಟ್, ಸ್ವಲ್ಪ ಎಪ್ಸಿಲಾನ್ ಲೂಸ್ಲಿ ಮಾತಾಡ್ತಾ ಇರ್ತೀವಿ. ಯಾಕಂದರೆ ಐ ಆಮ್ ನಾಟ್ ಟ್ರೈಂಗ್ ಟು ಪ್ರೂವ್ ಎ ಥಿಯರಮ್. ಜಸ್ಟ್ ಐ ವಾಂಟ್ ಟು ಕನ್ವಿನ್ಸ್ ದ ರಿಸಲ್ಟ್ಸ್ ಟು ಯು. ನನ್ನ ಕೆಲಸ ಏನು? ನಿಮ್ಮ ಬೆಂಕಿ ಹಚ್ಚೋದು. ನನ್ನ ಕೆಲಸ ಏನು? ನಿಮಗೆ ಬೆಂಕಿ ಹಚ್ಚೋದು, ವಿಚಾರ ಮಾಡ್ಸೋಕೆ ಹಚ್ಚೋದು ನನ್ನ ಕೆಲಸ. ನೀವು ವಿಚಾರ ಮಾಡ್ಕೊಂತ ನೀವೇ ಫಾರ್ ಎಕ್ಸಾಂಪಲ್ ನೀವು ಚಿಕ್ಕ ಮಗುದ್ರೆ ಅಂತ ಕೊಡ್ರಿ, ನಿಮ್ಮ ಮನೆ ಮುಂದೆ ಒಂದು ಆಕಳ ಓದ್ತಿರ್ತತೆ, ನಿಮ್ಮ ಮದರ್ ಏನಂತ ಹೇಳಿರ್ತಾರೆ ಅದರ ಚಿಕ್ಕ ಮಗುವಪ್ಪ ಒಂದು ಆಕಳ ಓತತ್ ನಿಮ್ಮ ಮನೆ ಮುಂದೆ, ನಿಮ್ಮ ಮದರ್ ಏನಂತ ಹೇಳ್ತಾರೆ ಅದ್ರನ್ನ? ಅಂಬಾ ಬಂತು ನೋಡು ಅಂತ ಹೇಳ್ತಾರೆ. ಏನಂತ ಹೇಳ್ತಾರೆ? ಅಂಬಾ. ಆಕಳ ಅಂತ ಹೇಳ್ತಾರೆ, ಅಂಬ ಅಂತ ಹೇಳ್ತಾರೆ. ಆಕಳ ಅಂತ ಹೇಳ್ತಾರೆ, ಅಂಬ ಅಂತ ಹೇಳ್ತಾರೆ. ಫಸ್ಟ್ ಅಂಬ ಅಂತಾರೆ, ಹೌದಿಲ್ಲ? ನಮ್ಮ ಸೈಡ್ ಅಂತ ಅಂಬ ಅಂತ ಕಲಿಸ್ಯಾರ. ಇಲ್ಲಿ ಕೂಡ ಆಲ್ಮೋಸ್ಟ್ 80 to 90 ಅಂಬ ಅಂತ ಕಲಿಸ್ಯಾರ. ಬಟ್ ನಿಮ್ಮ ಮದರ್ ಹೇಳಂಗಿಲ್ಲ, ಇದು ಅಂಬ ಅಲ್ಲ ಆಕಳ ಅಂತೇಳಿ. ನಿಮ್ಮ ಸೊಸೈಟಿಗೆ ನಾನು ಅಡ್ಡಾಡಿ ತಿಳ್ಕೊತೀನಿ, ನಾನು ಇದು ಅಂಬ ಅಲ್ಲ ಆಕಳ ಅಂತೇಳಿ. ಅದೇ ಟೈಪು ನನ್ನ ಉದ್ದೇಶ ಏನಿಲ್ಲಿ? ಅಂಬಾ. ನನ್ನ ಉದ್ದೇಶ ಏನು? ಅಂಬ. ನೀನು ಓದಿ 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 ಏನು ತಿಳ್ಕೊಬೇಕಾದ್ರನ್ನ ನಾನು ಏನೇನು ಪರ್ಪಸ್ಫುಲ್ಲಿ ಮಾಡಿನೋ ಅದ್ರ ನೀನು ತಿಳ್ಕೊಬೇಕು. ಅರ್ಥ ಆಯ್ತು ನಾನು ಹೇಳಿದ್ದು? ನಿಮ್ಮ ಅದರ ಕೆಲಸ ನಾನು ಮಾಡ್ತಾ ಇದ್ದೀನಿ. ನಾನು ಅಂಬ ಅಂತ ಹೇಳ್ತಾ ಇದ್ದೀನಿ, ಪ್ರತಿಯೊಂದು ಅಂಬ ಅಂತ ಹೇಳಿದ್ರೆ ನೀನು ತಿಳ್ಕೊಂಡು ಅದು ಅಂಬ ಅಲ್ಲ, ಅದು ಆಕಳ ಅಂತ ತಿಳ್ಕೊಬೇಕು. ಅರ್ಥ ಆಯ್ತಾ? ತಪ್ಪೇನೋ, ಎರಡು ಒಂದೇ ಹೋದಿಲ್ಲ, ಸೇಮ್. ನಾನು ಎಲ್ಲೆಲ್ಲಿ ಸ್ವಲ್ಪ ಸ್ವಲ್ಪ ಮಿಸ್ಟೇಕ್ಸ್ ಮಾಡ್ತಾ ಇರ್ತೀನಿ, ನೀವು ಒಟ್ಟಿಗೆ ಕೇಳ್ಬೇಕು ಅವ್ರು. ಓಕೆ, ನಾವು ಎ ಈಸ್ ರಿಪ್ಲೇಸ್ಡ್ ಬೈ ಸೆಟ್ ಆಫ್ ಆಲ್ ಪೀಸ್ ವೈಸ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಫಂಕ್ಷನ್ಸ್. ಪೀಸ್ ವೈಸ್ constant function. Now, so what is the theorem? Any continuous function can be approximated by piecewise constant function. What is the theorem? Any continuous function can be approximated. Continuous function is compact set. Well understood. It is can be approximated by piecewise constant function. ಇಲ್ಲಿ ನಾವು ಅರ್ಥ ಮಾಡ್ಕೋಬೇಕಾಗಿರೋದೇನು? How to produce a constant function from using neural network ಅಂತ ನಾನು ಆನ್ಸರ್ ಮಾಡಿಬಿಟ್ರೆ ಸಾಕು. ಸೊ ಏನು ಹೇಳ್ರಿ? What is the theorem I am using? Any continuous function can be approximated by a piecewise constant functions. Piecewise constant function ನಾವು ಹೆಂಗೆ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡ್ತೀವಿ ನ್ಯೂರಲ್ ನೆಟ್ವರ್ಕ್ ಅಂತ ನಾನು ಆನ್ಸರ್ ಮಾಡಿದ್ರೆ ನನ್ನ ಕೆಲಸ ಮುಗೀತು. ಇನ್ನೊಂದು ಸಲ ಹೇಳ್ತೀನಿ ನೋಡ್ರಿ. ಎನಿ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್ ಕ್ಯಾನ್ ಬಿ ಅಪ್ರಾಕ್ಸಿಮೇಟೆಡ್ ಬೈ ಪೀಸ್ವೈಸ್ ಕಾನ್ಸ್ಟೆಂಟ್. ಸೊ ನನ್ನ ರೋಲ್ ಏನೀಗ? ಹೌ ಟು ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಎ ಪೀಸ್ವೈಸ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಫಂಕ್ಷನ್ ಫ್ರಮ್ ಎ ನೆಟ್ವರ್ಕ್. ಫ್ರಮ್ ಎ ನೆಟ್ವರ್ಕಿಂದ ಪೀಸ್ವೈಸ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಫಂಕ್ಷನ್ ಹೆಂಗೆ ಕನ್ಸ್ಟ್ರಕ್ಟ್ ಮಾಡಿ ನನ್ನ ಆನ್ಸರ್ ಹೇಳಿಬಿಟ್ರೆ ನಂದು ಉದ್ದೇಶ ಮುಗೀತು. ಓಕೆ, ನಾವು ಸ್ಟಾರ್ಟ್ ಅವರ್ ಜರ್ನಿ. ಓಕೆ, ಸೊ ನಾವು ಯು ಟೇಕ್ ಎನಿ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್. ದಿಸ್ ಇಸ್ ಕಂಟಿನ್ಯೂಸ್ ಆರ್ ನಾಟ್? ಎನಿ ಗೆಸ್? ವಿ ಡೋಂಟ್ ನೋ ಎಕ್ಸ್ಪ್ರೆಷನ್. ಇಟ್ ಈಸ್ ಕಂಟಿನ್ಯೂಸ್ ಆರ್ ನಾಟ್? ಯಾರಾದ್ರೂ ಡಿಸ್ಕಂಟಿನ್ಯೂಸ್ ಅನ್ಸುತ್ತೆ ನಿಮಗಿದು? ಎದಕ್ಕೆ ಅನ್ಸಂಗಿಲ್ಲ? ಡಿಸ್ಕಂಟಿನ್ಯೂಸ್ ಅಂತ ಎದಕ್ಕೆ ಅನ್ಸಂಗಿಲ್ಲ? ಯಾರಾದ್ರೂ ಆನ್ಸರ್ ಮಾಡ್ಬೋದು? ಯು ಕ್ಯಾನ್ ಪೋಸ್ ನೋ ಚೈಲ್ಡಿಶ್ ಕ್ವಶನ್ಸ್. ಸೊ ಹೌ ಯು ಕ್ಯಾನ್ ಸೇ ದಟ್ ಇಟ್ ಇಸ್ ಕಂಟಿನ್ಯೂಸ್? ಎನಿ ಕ್ವಶನ್? ನಾವು ಲೂಸ್ಲಿ ಸ್ಪೀಕಿಂಗ್, ಅಂಬಾ ಅಂದ್ರೇನು? ಇಫ್ ಯು ಡ್ರಾ ಎ ಫಂಕ್ಷನ್ ವಿತೌಟ್ ಲಿಫ್ಟಿಂಗ್ ಯುವರ್ ಪೆನ್ ಆರ್ ಪೆನ್ಸಿಲ್, ದಟ್ ಈಸ್ ಆಲ್ಮೋಸ್ಟ್ ಕಂಟಿನ್ಯೂಯಸ್. ಈ ಗ್ರಾಫ್ನ ನೀವು ವಿತೌಟ್ ಲಿಫ್ಟಿಂಗ್ ಯುವರ್ ಪೆನ್ಸಿಲ್ ಡ್ರಾ ಮಾಡ್ಬೋದಾ ಇಲ್ಲ? ಮಾಡ್ಬೋದಾ ಇಲ್ಲ? ದೇರ್ ಫಾರ್ ಇಟ್ ಈಸ್ ಆಲ್ಮೋಸ್ಟ್ ಕಂಟಿನ್ಯೂಸ್. ನಾಟ್ ಆಲ್ಮೋಸ್ಟ್, ಇಟ್ ಇಸ್ ಎ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್. ಓಕೆ, ನಾನು ಹೇಳಿದ ಅಂಬಾಯಿಂದ ಆ ಕಡೆಗೆ ಹೋಗ್ಬೇಕು. ಓಕೆ, ಗುಡ್ ಗುಡ್. ಸೊ ನಾವು ದಿಸ್ ಈಸ್ ಎನಿ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್. ಓಕೆ, ಗುಡ್. ಸೊ ವಾಟ್ ಈಸ್ ಮೈ ಗೋಲ್ ಹಿಯರ್? What is my goal? How to construct a constant function. How to construct a constant, piecewise constant. Piecewise ಬಿಟ್ಬಿಡೋಣ, just a constant function. Constant function ಅಂದ್ರೇನು? Piecewise constant ಅಂದ್ರೇನು? I am considering compacts 0 to 1. Piecewise constant 0 to 1 ಡಿವೈಡ್ ಮಾಡಿರಿ, ಪ್ರತಿಯೊಂದು ಸಬ್ ಇಂಟರ್ವಲ್ನ ಕಾನ್ಸ್ಟೆಂಟ್ ಇರಬೇಕು. ಅದು ಏನು ಹೇಳ್ರಿ? 0 to 1. Now I am dividing into 3 parts. 0 to 0.4, 0.4 to 0.6, 0.6 to 1, 0 to 0.4, 0, 0.4 to 0.6, 1, 0.6 to 1, 0. It is a constant, piecewise constant or not? Yes, ಅಂದ್ರೇನು? 3 ಸಬ್ ಇಂಟರ್ವಲ್ಸ್ ಅದ, ಪ್ರತಿಯೊಂದು ಸಬ್ ಇಂಟರ್ವಲ್ನ ಕಾನ್ಸ್ಟೆಂಟ್ ಆಯ್ತದೆ. ಇಟ್ ಈಸ್ ನಾಟ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಓವರ್ ಥ್ರೂಔಟ್ ಇಂಟರ್ವಲ್ ಅಲ್ಲ. ಓಕೆ, ಗುಡ್. ದಿಸ್ ಇಸ್ ಕಾಲ್ಡ್ piecewise constant. Now here crux point is how to construct constant function from neural network. Okay, now start. No matter what the function, there is guaranteed to be a neural network, so that every possible input x, the value f of x for some closed approximation epsilon, okay, is output from the network. This is input, f of x is the output of the neural network. This is the hidden layer. This is the hidden layer. Okay, good. So now, here, hidden layer may contain, in the previous case, hidden layer contains how many neurons? 3 neurons. Here, input layer contains how many neurons? 3. Hidden layer contains how many neurons? 5. Output neuron contains how many neurons? 2. Okay, it may contain any like that. Okay. This result is a function from many inputs x1, x2, xm and many outputs. These are the 2 outputs. For instance, here is the network computing with m equals to 3. What is m value? 3 inputs and outputs 2. Okay. So now X. I am considering only one input, two input neurons, one output. Now, to build insight into how to construct a network to compute F, let's start with a network containing a single hidden layer with two hidden neurons and an output layer containing single output neuron. So now here it's important. Just watch this video. Okay. What you found in this video? ಇನ್ನೊಂದ್ಸಲ ಪ್ಲೇ ಮಾಡ್ತೀನಿ ನೋಡ್ರಿ. What you found in this video? So now weight increasing. Now bias, threshold value increasing. ಇನ್ನೊಂದ್ಸಲ ವಿಡಿಯೋ ನೋಡ್ರಿ. ಈ ವಿಡಿಯೋ ಅರ್ಥ ಆಯ್ತು ಅಂದ್ರೆ ಮುಗಿತು, ಏನಿಲ್ಲ, ನಥಿಂಗ್ ಫನ್. I am changing the weights W. I am changing the bias threshold value. Okay. So what you found here is a threshold value. Andrenu, whenever value of x is less than 0.3, its value is 0. Whenever x is greater than 0.3, its value is non-zero, and it is threshold value. So we have constructed an activation function. If I am changing the weights and basis, it will produce the threshold value function, threshold function. Okay. Good. So now this is the activation sigma of x. It is nothing but 1 divided by 1 plus e power, weight value is 999 and x bias is 400, minus into minus plus. Okay. This is a activation function. This is called activation function. We can simplify our analysis quite a bit by increasing the weights so much that output really is a step function. Output is really a step function. To a very good approximation, below we have plotted our output from the hidden neuron. W is 999. Note that this plot is static and the bala changes angle. Okay. You can't change the parameters as weights. Okay. So here weights, one neuron, one bias. So now this is almost what kind of function? It is nothing but piecewise constant. It is nothing but piecewise constant. Yes or no? Otherwise, it is a threshold function. Okay. So now, what is the W here? 999. What is the B? Minus 400. Okay. Good. Oh, question: at what value of x does the step occurs? Under x value ಏನidre 0 ಇಂದ non-zero jump ಹಿಡಿತೈತೆ. ಅದು important. Okay. Good. So answer is S equals to minus B W. In the previous case, what is B? Minus 400. Minus S by W, 999. Okay. Good. So now, where is the jump occurs here? At 0.4. At 0.4, jump occurs. So now, just I am adding two functions here. S1 jump occurs 0.40, jump occurs at 0.6. Okay, and combining these two, it is a piecewise constant function. Between 0 to 0.4, 0, 0 to 0.6 non-zero and beyond is also non-zero. So this produces a threshold value function at 0.4. This neuron produces a 0.6. Now linear combination of these. Okay, now this is our step function. Between 0 to 0.40, 0.4 to 0.6, this portion is non-zero and beyond it is 0. So now we have found that weights and bases such that 0 to 0.40, 0.4 to 0.6 non-zero, beyond 0.60, we constructed constant function. This is called a bump. Bump function. So speed breaker irutate adar nanತರ bump anta. Why it is bump? So plane irutate, next height matte down madutade, that is called a bump. Okay, good. See here bump occurs. Where the bump occurs? Between 0.0 and 0.60. Bump occurs 0.4 and 0.6. So now S1 0.4 and W1 is like this. And so what might be the bump height? What is the bump height? Where the bump occurs, what is the bump height? Two parameters. What we are considering here? Where the bump occurs, what is the height of the bump? What is the height of the bump here? 0.6. Okay. Good. Now I want to produce two bumps. Maybe height, maybe down. Okay. So now 0.4, 0.6 ಅಂದ್ರೇನು ಇದರರ್ಥ ಏನಾಗ್ತದೆ between 0.4 and 0.6, between 0.4 and 0.6, what is the height? Minus 1.2, downside ಆಗುತ್ತೆ. How much? 1.2. Check it here, 1.2. Next, this network produces a bump between 0.7 and 0.9. This is 0.7 and 0.9. Bump up height how much? 0.3. Now if I am adding neurons, how many neurons here? 4 neurons. Any two neurons produces a where the bump. Two neurons produces a where is the bump. Where is the bump? Between 0.4 and 0.6 with height minus 1.2. These two neurons produces another bump between 0.7 and 0.9 with height 0.3. You can produce in any number of bumps of with respect to heights. So now I have considered 5 bumps. I have considered how many bumps? 5 bumps. 5 bumps andre artha 0 to 1 is divided into how many equal parts? 5 equal parts. Andre ಏನು ಅರ್ಥ? 0 to 1 by 5, 1 by 5 to 2 by 5, 2 by 5 to 3 by 5, 3 by 5 to 4 by 5, 4 by 5 to 1. Okay. Now 5 bumps between 0 to 0 point andre 1 by 5 andre 0.2. 0 to 0.2 a bump of height 0.6. Next 0.2 to 0.4 of height down 1.1. Next 0.4 to 0.6 of height 0.8. Next 0.6 to 0.8 of height 0.7. Next 0.8 to 1.0 0.3. You can ಇದರಿಂದ ಈ ಡಯಾಗ್ರಾಮ್ ನಿಮಗೆ ಏನು ಅರ್ಥ ಆಯಿತು? ಬಿಟ್ವೀನ್ 0 to 1 ನೀವು ಎಷ್ಟು ಈಕ್ವಲ್ ಪಾರ್ಟ್ಸನ್ನು ಮಾಡಿಕೊಡ್ರಿ ಪ್ರತಿಯೊಂದು ಸಬ್ ಇಂಟರ್ವಲ್ನಾಗ ಯು ಕ್ಯಾನ್ ಪ್ರೊಡ್ಯೂಸ್ ಎ ಬಂಪ್ ಆಫ್ ಯುವರ್ ಓನ್ height up and downs. So now it is, what is that function I have considered? 0.2 plus 0.4x square plus 0.3x into sin 15x plus 0.05 cos 50x. This is a function. Now I am going to approximate this function by using neural networks. So now ಇಲ್ಲಿ ಸಮಸ್ಯೆ ಏನು? I can produce the bumps. Height ಹೇಗೆ ಮಾಡಬೇಕು ಅದು ಇಂಪಾರ್ಟೆಂಟ್. Height important. What might be the height of the function? Just you are sampling the function. The sampled value act as a height of a bump. The sampled value act as a height of a bump. So ನಾವು ಇದನ್ನ ಜಾಮೆಟ್ರಿಲಿ ಹೆಂಗೆ ಎಕ್ಸ್ಪ್ಲೇನ್ ಮಾಡ್ತೀವಿ ಅಂದರೆ ಇನ್ವರ್ಸ್ ತಗೊಂತೀವಿ ನಾವು. Weighted sum equals to what? Weighted sum plus bias equals to output. Now inverse, weighted sum equals to sigma inverse composed of this will help me to compute the, this will help me to decide the bump's height. Bump's height. Okay, good. So now I know, so number of subintervals of your own choice, and each subinterval having a bump, and height ಹೆಂಗೆ ಡಿಸೈಡ್ ಮಾಡುತ್ತೆ, ಸಿಗ್ಮಾ ಇನ್ವರ್ಸ್ ಕಾಂಪೋಸಿಟ್ ಎಫ್ ಆಫ್ ಎಕ್ಸ್, ಯು ನೋ ಎಫ್ continuous function, you know f sigma. What is sigma? Sigma of x is a sigmoid function, 1 divided by 1 plus e power minus x. It is invertible function. Okay, compose. So now this is the one example I have considered. Says these are the heights. You can vary. These are all my heights. Okay. So now, so we have approximated sin x function between minus pi to pi using neural network. Output is given below. So blue thick line indicates approximation, and almost orange looks like a actual function. Both are on, and it is highly non-linear. Sin x function is highly non-linear. We have approximated sin function using neural network. Okay. So what universal approximation? It has 3 components. What are those? Approximate by step functions we have done. Next, neural network is a sum of step functions. Neural network has sum of step functions. We are adding all the bumps. Okay, good. And refine the approximation. Approximation refine ಮಾಡಬೇಕಂದ್ರೆ number of bumps ಕಡಿಮೆ ಇದ್ರೆ ಒಳ್ಳೆಯದು, ಜಾಸ್ತಿ ಇದ್ರೆ ಒಳ್ಳೆಯದು. You are approximating continuous function by a constant. ಅಂದರೆ ಇಂಟರ್ವಲ್ ಸೈಜ್ ಕಡಿಮೆ ಇದ್ರೆ ಒಳ್ಳೆಯದು, ಜಾಸ್ತಿ ಇದ್ರೆ ಒಳ್ಳೆಯದು. ಇಂಟರ್ವಲ್ ಸೈಜ್ ಕಡಿಮೆ ಇದ್ರೆ ಒಳ್ಳೆಯದು, ಜಾಸ್ತಿ ಇದ್ರೆ ಒಳ್ಳೆಯದು. ಜಾಸ್ತಿ ಇದ್ದಷ್ಟು ಒಳ್ಳೆಯದು. ಅಂದರೆ ನಂಬರ್ ಆಫ್ ನ್ಯೂರಾನ್ಸ್ ಜಾಸ್ತಿ ಆದಂಗೆಲ್ಲ ಬೆಟರ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಸಿಗುತ್ತೆ. ಓಕೆ, ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಬೈ ಸ್ಟೆಪ್ ಫಂಕ್ಷನ್ಸ್. ನೆಕ್ಸ್ಟ್, ದಿಸ್ ಈಸ್ neural network function. This is f hat of x, a neural network function. This is nothing but linear combination of output. This is nothing but output of the neural network. So now m is a number of neurons. M is the number of neurons. Okay. 5 neurons ತಗೊಂಡಿದ್ದೀವಿ ನಾವು. 5 neurons 5 bumps. 10 ತಗೊಂಡ್ರೆ 10 bumps ಸಿಗ್ತಾವೆ. M is infinity. Infinity ಸಾಧ್ಯ ಇಲ್ಲ. M is large. Okay, good. So now we are going to get better approximation. Good. So now these are the limitations. Okay, what are the limitations of UAT? UAT does not preserve how to the right weights or long it will take to train a neural network for a given problem. One problem ಕೊಟ್ಟ ತಕ್ಷಣ, so it will take, what are the limitations? These are all the limitations. So right weights immediate, ಅಂದರೆ weights ಕಂಡುಹಿಡಬೇಕು ಅಂತಂದರೆ ಭಾಳ ತ್ರಾಸಾಗುತ್ತೆ. Just not like that AND gate. AND gate ನಾವು ಭಾಳ ಸಿಂಪಲಾಗಿ ಕಂಡುಹಿಡಿದು ವಿತೌಟ್. ಸೊ ಫಾರ್ ದಿಸ್ ಒನ್ ವಿ ಆರ್ ಗೋಯಿಂಗ್ ಟು ಯೂಸ್ ಗ್ರೇಡಿಯಂಟ್ ಡಿಸೆಂಟ್ ಮೆಥಡ್ ಟು ಫೈಂಡ್ ದ ವೇಟ್ಸ್. ಆ್ಯಂಡ್ ಗ್ರೇಡಿಯಂಟ್ ಡಿಸೆಂಟ್ ಎರರ್ ಅಂದರೆ ಬೇಕು. ಎರರ್ ಅಂದ್ರೇನು? ಅಪ್ರಾಕ್ಸಿಮೇಟೆಡ್ ವ್ಯಾಲ್ಯೂ ಮೈನಸ್ ಎಕ್ಸಾಕ್ಟ್ ವ್ಯಾಲ್ಯೂ. ಬಟ್ ವಿ ಹ್ಯಾವ್ ಟು ಮೆಜರ್ ದ 8. ವಿ ಆರ್ ಕನ್ಸಿಡರಿಂಗ್ ದ ನಾರ್ಮ್. ಇನ್ ದ ನಾರ್ಮ್ ಮೀನ್ಸ್ ವಿ ಆರ್ ಕನ್ಸಿಡರಿಂಗ್ ದ ಎನಿ ನಾರ್ಮ್ ಈಸ್ ಇಮೇಡ್. ಬಟ್ better to have a smooth norm. It is differentiable. We are going and differentiable and Hilbert space ಆಗಬೇಕು. What is the norm for the Hilbert space? Any guess? Hilbert space norm ಯಾವುದು? Euclidean norm. Norm x ಕೆಳಕ್ಕೆ 2 ಅಂತ ಬರಿತೀವಿ ನೋಡಿ, ಅಂಡರ್ ಸ್ಕ್ವೇರ್ ರೂಟ್ ಆಫ್ x1 ಸ್ಕ್ವೇರ್ ಪ್ಲಸ್ x2. ಸೊ ದಟ್ ಈಸ್ ಗೋಯಿಂಗ್ ಟು ಬಿ ಗ್ರೇಡಿಯಂಟ್ ಡಿಸೆಟ್. ನಮ್ಗೆ ಈಸಿಯಾಗಿ ಅಪ್ಲೈ ಮಾಡ್ಬೋದು ಅದಕ್ಕೆ. ಓಕೆ, ಸೊ ದಿಸ್ ಆರ್ ಆಲ್ ದ ಪ್ರಾಬ್ಲಮ್ಸ್ ಅಸೋಸಿಯೇಟೆಡ್ ವಿತ್ ದ ಥಿಯರಮ್ ಅಪ್ಲೈಸ್ ಟು ಫಂಕ್ಷನ್ ಅಪ್ರಾಕ್ಸಿಮೇಷನ್ ಗಿವನ್ ಟ್ರೈನಿಂಗ್ ಸೆಟ್, but it does not guarantee how well the network will generalize to new or unseen data. Okay, ಅಂದರೆ ಇಲ್ಲಿ ಟ್ರೈನಿಂಗ್ ಆ್ಯಂಡ್ ಟೆಸ್ಟ್ ಅಂತ ಎರಡು ಡಿವೈಡ್ ಮಾಡ್ತೀವಿ. ಅದೆಲ್ಲ ಮೆಷಿನ್ ಲರ್ನಿಂಗ್, ಡೀಪ್ ಲರ್ನಿಂಗ್ ಭಾಳ ಹೆವಿ ರೋಲ್ ಇರ್ತೈತೆ. ಇಲ್ಲಿ ಜಸ್ಟ್ ನನ್ನ ಉದ್ದೇಶ ಏನು, ಥ್ರೂ ಜಾಮೆಟ್ರಿ ಹೌ ಟು ಪ್ರೊಡ್ಯೂಸ್ ಎ ನೆಟ್ವರ್ಕ್ ವಿಚ್ ವಿಲ್ ಮಿಮಿಕ್ ಸ್ಟೆಪ್ ಫಂಕ್ಷನ್. ದಟ್ಸ್ ಆಲ್. ಇಷ್ಟಾದರೆ ನಿಮಗೆ ಆಲ್ಮೋಸ್ಟ್ ಯು ಕ್ಯಾನ್ ಪ್ರೊಸೀಡ್ ಫರ್ದರ್. ಓಕೆ, while theorem assures that such approximation exists, it does not provide insights on how to efficiently train the network. Okay, summary, what we have done here. Okay, good. So artificial neural networks have emerged as a powerful tools for modeling complex non-linear relationships in data across wide range of domains. The universal approximation provides a strong theoretical foundation for their defectiveness. UAT assures existence, ಅಂದರೆ ನ್ಯೂರಲ್ ನೆಟ್ವರ್ಕ್ ಎಕ್ಸಿಸ್ಟ್ ಇದೆ ಟು ಅಪ್ರಾಕ್ಸಿಮೇಟ್ ಎ ಕಂಟಿನ್ಯೂಸ್ ಫಂಕ್ಷನ್. just like this one, yadu Cauchy sequence is convergent. Every Cauchy sequence is convergent, but it fails to give the limit point. Okay, good. So now these are all references, and this is an excellent one. Almost all material is from this author. Okay. Okay. So I recommend, this is excellent material to understand this one. I borrowed almost all material from this one. Okay. You can take this. No. Sure. This one. Okay. Over. So these are all survey on universal approximation theorem. Just thank you. Okay. Any doubts? I am ready to discuss with you.
Okay. Any questions from the audience? Please ask.
Yes. So for just I have this. Any continuous function can be approximated piecewise constant functions. Any continuous function can be approximated piecewise constant. So whenever you are drawing a graph, your subintervals, below the subinterval, we are approximate that function by any one of the sample. That is how Haar wavelets do that job. Same thing, Haar wavelet place is replaced by neural network. Okay. Here activation function I told you, sigma of x to 1 divided by 1 plus e power minus x. You can replace that sigmoid function by wavelet. That's why the name, sorry. Yes, yes. Yes, you can use any kind of wavelet as a activation function, but it must have some significance. It has to produce constant over some interval. So that is a separate topic, wavelet neural networks, WNN, wavelet neural. What is the important there? Input layer, output number of same, only replacing is, you are replacing activation function by a wavelet. For example, threshold less than 0, that's a wavelet. Okay.
Okay.
Any other doubts?
No questions? Then I like to ask one question.
Yes, sure, sir.
See, we are generating rainfall data at various locations in Bangalore.
Yes.
Can you use this data during floods? This artificial neural network.
Sure. So, okay, sir, I will explain what I have done. What I have done. So we have done one thing in the, whenever data is there, so only thing is we have to concentrate what it says. So is there any person from Koppal district? Koppal district? Nobody is there. So a place we have, we considered a place, Chilavadigi, surround 15 kilometers from Koppal, and we have collected samples, photographs of 3 crops, groundnut, onion, chilli of 3 seasons. We collected the photographs, we have done processing work, and we have used the artificial neural networks to predict the nature of diseases. So now, and published 3 data as a 3 data articles and smart agriculture technology, sir. So same thing, I am interested in agricultural sciences related work. So whenever data is there, only thing is that we must have the domain knowledge, then we can easily apply it, sir. Yes.
Okay, thank you, sir, for excellent presentation.
Okay, sir.
Thank you.
Shall I switch off, sir? Okay.
Thank you so much, sir,
Switch off,
for chairing the session. Okay, sir. Thank you, sir.
Now, let's move on to the next session. I call upon Soundarya to proceed the session.
Good afternoon, everyone. Dr. A. Padmanabha Reddy is a VGST young scientist and assistant professor in the Department of Mathematics at Vijayanagara Sri Krishna Devaraya University, Ballari, Karnataka. With over a decade of experience since 2012, Dr. Reddy specializes in wavelet analysis, numerical analysis, differential equations, and mathematical imaging. He has guided 7 PhD scholars and has completed a notable research project on wavelets and their scientific computing, funded by the Karnataka government. He has published around 30 research articles in reputed journals and completed 4 certificate courses in advanced mathematical and data science topics. Dr. Reddy has been invited speaker at over 30 national and international conferences and workshops, contributing significantly to mathematical research and education. With this brief introduction, I request Padmanabha Reddy sir to chair the session. Thank you.
Hello, hello, Dr. Goodwin sir. ಇನ್ನು ಬಂದಿಲ್ಲ ಇಲ್ಲ ಅವರು ಹಲೋ ಅಂದರು ಇದೆ ಸರ್ ಪೆನ್ ತೋರಿಸ್ತಾ ಇದೆ ಹಲೋ ಡಾಕ್ಟರ್ ಗುಡ್ವಿನ್
Hello? Hello?
Yes, sir. I think he joined. Hello, namaste, sir. Namaste. Yes, he has come. Yes.
Yeah, good morning.
Yes, sir, please. Sir, I am.
Good morning. Can you hear me?
Hello, sir. I am Padmanabha Reddy. I am chairing your session, sir. This session. I am happy to introduce your resume to audience present here and in this hall and those who have joined offline and online. Dr. Godwin Chidi Ugwandi is a senior lecturer in mathematics at University of Eswatini, South Africa. He holds a PhD in functional analysis and has research interest in fixed point theory, variational inequalities and bilevel optimization, with awards including Nigerian Mathematical Society Special Award and EP Udohua Memorial Foundation Award. He voluntarily teaches high school students for the Pan-African Mathematical Olympiad. Just like our Indian Mathematical Olympiads, he voluntarily teaches high school students to participate in the Mathematical Olympiad. So I am happy to invite you, sir, for your valuable talk and I am hand-overing this session to you, sir. Thank you.
Yeah, thank you so much. And good morning, everyone. So I am honored to present my research and what we have been doing for a while in this conference. So I thank you so much for inviting me for this international conference. So first of all, I will share what I want to discuss with you people now. Can you see my screen?
Yes, sir.
Okay, today I want to discuss what we have been doing for a while, exploring inertial projection and contraction methods for solving a variational inequality problem in Banach space. Actually, this method, projection and contraction method, is a very vast method of solving variational inequality, but mostly in finite dimensional and the Hilbert space. And the inertial term here is all about trying to speed up the project, the method, the convergence of the method. That is the essence of the inertial, is a kind of momentum that speed up the convergence. So what we are trying to see here is how do we extend this method to a general space called the Banach space. And the part of this work, what we are going to discuss today is a joint work with my PhD student, Maluleka, and Apan is a co-supervisor, and Abbas is one of my collaborators. And Abdurrahim Khan, who is based in Pakistan. Recently, he was in Saudi Arabia for a long time, but now he's in Pakistan, his home base. One of my mentors, actually. So first of all, let's try to look at what we call a relation that we call variational inequality problem. That's when you have a feasible set C, which is a closed and convex. At any point we pick in a set C. And here our space, we are looking at the general Banach space. That if the pairing now here, this is not binary inner product because we are in a general Banach space, so it's a pairing. The pairing of the point, any other point in C, the difference of any other point in C and X star must be greater than equals to 0. This is what we call a variational inequality problem. Trying to solve a problem like this. And all the points X that satisfy this kind of relation is now what we call the solution, which we always denote as Vi of C of A, where A is the operator. This A, we are going to concentrate on the nature of A. Depending on this problem we are solving, A most of the times is strongly monotone. And when it's strongly monotone, we are happy we can achieve uniqueness of solution, but which is also a weakness to the problem because of some strong condition that a monotone imposes. A strong monotone imposes in a problem like some research problem, more especially via partial differential equation or solving some optimization problem. That is not always, or they are not always strongly monotone. The operator is always monotone or pseudo-monotone. So that is the problem. Then the next is, let's try to know the significance of this problem, which first we have seen the existence of equilibrium. We can apply it in solving some equilibrium problem, trying to stabilize market price and in a resource allocation. We can also apply it and also planning production and in terms of transportation method. We can apply the variational inequality problem or solution of variational inequality problem to establish the shortest distance in terms of transportation problem. Now, let us look at the basic problem we normally have when you have a smooth space. That is a function. A function is differentiable. That's what we mean by smooth here. On a closed interval A, then we want to determine the minimum point of the function. You now say to determine the minimum point x naught, then this three condition is always arises. When the point is in between the interval, then the f prime is equals to 0. f prime of x naught is 0. But if the point is at the lower a, if the minimum point is a, then f prime of that point is always greater than or equals to 0. But looking at these three conditions, we now see that this three condition is nothing but the relation we have here, which is a variational inequality problem. So solving a problem like this is the same thing as solving a variational inequality of this kind. And we know that this kind of problem is applied in many areas of machine learning, descent method, and most of the optimization problem. So that is one of the simplest application I can show. Now, our own goal, the major goal is how do we solve this problem, the method of solving the variational inequality problem. So we have two basic problems, what we call regularized method and projection method. Then in the regularized method, we always lack a string monotonicity, or the operator involved, we lack what we call lattice continuity. So our major goal here is to go via projection approach. So that is what we are going to discuss now. But before we introduce the projection approach, we must first of all understand the metric or projection operator. When we say that, what do we mean by projection? How do we project? Then we try to use a simple Hilbert space that this operator PC of x, which we call the projection of x, where x is in a Hilbert space. Picking any point in Hilbert space, our major goal is how do we drive this point to C, which in a nutshell, this relation is just the definition of projection operator. And this hold, if and only it will hold now. So this is a unique relation in trying to relate inner product method to projection operators, Z now. With this, we try to see the relationship between projection and the fixed point, or between the VIP and fixed via this projection. In answer that solve, when you have an operator A, I will have included a picture here so that you understand actually what we are trying to do here. So the relationship between 2 and the fixed point problem, when we solve this, we now see that finding a fixed point Z of this projection is the same thing as solving the variational inequality with respect to Z. This is one relationship between a fixed point problem and variational inequality problem. Now, with this, we can now define the projection method of solving variational inequality via fixed point approach. Then, that is this we now have here. Finding Z in C such that Z in the projection of where I is identity, this term here is related to A, where A is an operator, sometimes strongly monotone, in advanced application, monotone or pseudo-monotone. Then we start from a strongly monotone, which we call the classical projection method, which was introduced in 1966. And we now define the kind of iteration method to approximate the points that will now be the solution of this A, where A is a strongly monotone operator. Now, this is what we call step size. And this step size depends on this eta, where eta is the constant for the strongly monotone. So this is one of the methods of solving a variable inequality, which we call the projection method. But here now, the problem of this A being strongly monotone is because strongly monotone, not that it's too bad, but it tried to a kind of not accommodating most of the operator that involves with the partial differential equation or some important aspect of optimization problem. Now, this is the definition. Here we'll try to introduce the definition of strongly monotone operator and the monotone operator when this guy is now. Okay, now let's see the weakness of a strongly monotone. Let's consider C as the R2 now. So in finance, the two-dimensional plane. Then we talk about the operator as what? A rotation. That we rotate pi over 2, that is 90 degree, anti-clockwise direction. We now see that this A, which is a rotation of an angle 90 degrees, is a monotone. And here the solution is 0. But we now see that but it's not convergent. So when it's a monotone, it's not convergent. Using the classical projection method, which I think I included some things here. So the mathematical aspect, we see that when the rotation is pi, then we have from the general method of rotation of an operator from linear transformation. That is where we get this. That we now have minus x2 comma x1. When we rotate x comma 1 to this, we know the general formula. Then trying to solve find this relation where this is an inner product, then the mathematical aspect to see this is 0. We get 0, which from the definition of monotonicity is talking about greater than or equals to 0. So weakly we can now say that this is a monotone. The rotation is a monotone. Now let us now apply this to the classical projection method. Remember that our C, which is close and converse, is R2. Since C is R2, we now see that it will project every point here to itself. So this projection is just identity operator. So that is why we have this C. So when we now define a sequence, since we are in R2, we now define it as the first component and the second component xn2. Then we rotate that. We rotate any sequence in C. Then the rotation will be from the definition of rotation will be of this form. Then if we now iterate xn plus 1, based on the classical definition of projection method, it's not difficult to see that we have this. And from here now, the last relation, you see that none of xn plus 1 will be strictly greater than none of xn for any tau greater than 0. What does this say? We know that norm is bounded below by 0 from the definition of norm. And since norm is bounded below by 0 and bounded above, because it shows that now norm of xn plus 1 is strictly increasing, but is not bounded above. Then from here, we can now establish the array sequence does not converge. Since we are in a finite dimension, we can conclude that xn does not converge also. Because of this, we can now see why we say that when looking at the projection method and they're trying to get operator that are more general, that the projection method will not be of help. Then it can only help when the operator is strongly monotone. So that is the essence of this, why strongly monotone is considered as a restrictive. That the summary of this here is that though the strongly monotone guarantee uniqueness of a solution, but one, we know in application, like in a partial differential equation, where we have a multiple equilibria or multiple points of solution, then it will not be easy to identify which solution is more perfect, because applying the strongness of monotonicity will not hold, and also it will not help us to discuss more general operator like monotonicity and strong monotonicity, which are rich in other area of optimization and equilibrium. So with this, we now see that there is to modify projection method. That is why Kopovich in 1976 introduced what we call extra-gradient method. This extra-gradient method, what he did is coming to the, just he modified the projection method by introducing another step. But it now involves two projection. So that is this P of C and the T of C. This helped us to solve the problem of a projection method, but depending on the nature of operator, if the operator is simple, then we don't have problem. But we know in application, most of the times, the nature of operator we have may not be simple. And finding the projection of that kind of operator sometimes is not easy. It takes a lot of time. And trying to approximate solution, we always try to minimize the time of approximation. When we now talk about the rate of conversion, that is, I'm now trying to discuss the weakness of this method now. Even though it helps us to solve some problem, to accommodate some larger, more larger operators, monotone and pseudo-monotone, but it still have some problem. Now, we are going to see how this will solve the if A is rotation, as we have seen previously, that the sequence diverge. Using the upper fish, that is a gradient method, we found out that this will converge with the rotation pi over 2, which I included this place to see the beauty. So the same space at R2, then we have PC as identity. Then when we iterate, we have xn plus 1, the extra gradient method will now be this. The finding norm of xn, we now see we arrive at this, which from this place, that's the norm squared now. The norm of xn is now this, and this is less than the norm of xn plus 1 will now be less than what? Norm of xn for any tau less than 1, which is so beautiful. Why? Because we are in finite dimension. Since we are in finite dimension and the norm is bounded below by 0, what can we say? It means that, and this is a ray sequence. When a sequence is bounded below by 0 and is strictly decreasing, then it means the norm is now what? So when a sequence is bounded below by 0, and the sequence what? Decreasing, and this one is strictly decreasing, then norm of xn converges to what? To 0, to the lower bound, which is also the infimum. Now, since it's converged to 0, we cannot say that xn converges to 0. All we know here is that the norm of xn converges to 0. But we have something that are good here because we're in finite dimension. And if a norm of xn converges to a point in finite dimension or to 0 now, then the sequence itself converges to that point because of the nature of finite dimension. So with this, we hope to see the picture, the trajectory, the movement. Now see the movement, how this cluster still within, then clustering, and it's what? Converging, but not speedily, but it's actually converging to 0, which shows that actually this converges to 0. Okay. Now, due to the full projection of a gradient method, which we have talked about the costly implication in trying to iterate or in trying to approximate the solution, then there will be a need to modify the extra gradient method, which the need first is by Francois Eckhart, which we call subgradient extragradient method. What they did is that in the second projection, instead of the projection onto the physical, the sea, they now define the half space Tn. They now define the Tn. What is the essence of this Tn? If you watch the Tn, the definition of Tn, you see that it is what? Based on what we have already. The xn minus tau axn is already here, which is already computed. Because we are talking about the costly computation, the cost of computation, the time taken to compute. And here we have yn already. So finding this half space Tn will not be as difficult as we are in C. So what we call half space, that's the first. Then we try to see the nature, they are almost the same. The trajectory of a gradient using A as a rotation pi over 2. They are still the same. But the rate of convergence is faster here when we look at this place. Then another one is what we call Send method. What Send did is Send tried to remove totally the second projection. We tried to remove totally the second projection to introduce what we call the residual. So, and with this, we still try to see the nature using a simple rotation, a pi over 2, and look at it that is also converging to 0. Then we must note that this subgradient by sensor and spread, it have many numerous applications, and also there are different ways they have modified it, but both in Hilbert and Banach space. Now, projection and contraction method. The projection and contraction method also try to look at only one projection and produce a residual of this kind. And also, instead of the method of Send, we now talk about another residual of this kind using a D. So where you find the step size as an eta n, which this, though not so much, the difference between this, the rate of convergence with Send, they are not much, but it's also another method But the problem here now, the projection and contraction, is for a long time, it has only been in Hilbert space. We have not seen how can we take it to Banach space. And that is the essence of this work. And this work, not only the next slide, this is the convergence, the trajectory using the operator also. Then, the projection and contraction method, we are going to concentrate more on projection and contraction method, where they introduce a momentum. This momentum we call inertial, it helps in speeding up the convergence rate. That's the essence of inertial in a iterative process, which it has numerous applications in optimization in the equilibrium problem. So our major goal is how do we take this method to general Banach space? Because for long we have seen both extravagant method and the same method, the method are being used in general Banach space, but not projection and contraction. What is the problem? You now see that there is always a constraint on the step size, which our major goal is now how do we boycott it to take it to Banach space. So for us to do that, but we now see, look at this is a good picture of inertial and not inertial. So when you look at this graph and this graph, this one looks more better. But the issue is the essence of this momentum. Because this momentum will overshoot because of the nature of speeding up. It will overshoot. And that is why this now looks like not going clustering, going close to zero, but the nature of the overshoot. If we take this up to 100, you see that this will be clustering, coming close to this to zero. Because of the nature of the removed rotation, we try now to see the trajectory comparison between inertial and non-inertial. So the initial behavior. See that the initial behavior, the non-inertial will also remove it smoothly, trying to correct. But for inertial, the momentum what we call extrapolation always try to converge faster with a down. With a down is that is this alpha n. That is what controls those inertials. Then the rate of convergence. This is the importance of inertial. This always slowly progress with a stable step. Then this accelerates, but it accelerates sometimes it will shoot out. But depending on the residual try to control it for stabilization. And for rotation rate, for this example, you see what's happening. And so our major goal in inertial is this fast acceleration and the faster convergence. That is the most important aspect of inertial, which we are going to look at. So the question of interest. So as I have said earlier, the subgradient, extragradient, and insert method are being applied in solving a problem both in Hilbert and Banach space. But we have not seen any result of a projection and contraction method in literature in a more general space like Banach space. So the question now, can we employ this projection and contraction method in solving variational inequality Banach space setting? Not only that, how do we do that? Can we produce an inertial that is Not only that we introduce it, but trying to speed up the convergency using inertial and hyper method. These are the method of speeding of convergence and achieving strong convergence. Then we try to look at uniform converse ray Banach space, which is also uniformly. So before we do that, we try to see some basic information. We try to see key elements. This looks like folder lectures. Working is what we have our normal lectures. In the monotone, we have to note that this is not an inner product, but a pairing in a dual space. And also the variation, the pseudo monotone process and sequentially with continuous process of A. Then we try to define the generalized duality mapping into uniformly convex space. Then P is we have a normal duality map. Then we employ Bregman distance, which is defined of 10. We have seen we know the importance of Bregman distance in the studying of equilibrium or descent method in Banach space. So because our space is uniformly convex, we are going to now use these terms of because this is strongly monotone, with in place of F in 10, which will define the relation of the Bregman distance in terms of uniformly convex as this. So these are the identity, 3-point identity of Bregman. We are going to employ this. And also in Bregman, in the sense of Bregman, the projection is defined in this form, which with relation to in a dual pairing, this also hold point Z is the projection of X onto Bregman projection of X onto C. Then these are some lemmas that help us to achieve our results, most especially this three. So these are another, the Young's inequality actually help us in the sense of the inertial method and also this relation 19 and 20. Then with this, we now make an assumption for our algorithm. But if E is P uniformly convex, real Banach space, which is also uniformly smooth, then we have operator that is fully monotone, but P minus 1 element is continuous on A, and A is weakly sequential continuous. Then we now have some parameters, mu n that is in this 0 of P. This phi P is because of the nature of E here, that is uniformly, which we know that the norm of the norm P is strongly monotone. So this is the constant of strongly monotone. And another parameter which are very essential for the sense of a man or hypernitration. That's the norm of alpha n is 0, and the infinite sum must be also guaranteed. Then our algorithm. Then our algorithm will pick 2 points arbitrarily and pick a theta in this. Then this theta n bar will help us to control the initial condition. And now this is the classical, in the nature of classical projection method, but with an initial operator now. Now we try to add some parameter that will help us, the dn, which control the projection problem, instead of adding another projection, which we have seen in a senk method. Then here we apply high pan method in order to achieve a strong convergence of this. So what we really had to make this happen in the general Ghana case is this relation. So that was the major issue why projection and contraction method was difficult to establish in general Ghana case. But with this, I know this has been published in Artisan Journal of Mathematics, some part of this, which I did with from the beginning, the collaborator and my PhD student. So I know very soon a lot of people will be coming out under this to modify, because I know there will be another way in order to modify this to get a weaker condition. So, in order to study the comparative analysis, we first of all, using the lemma of 1920, we first of all established this relation, which helped us to show actually that if dn is equals to 0, then we have this, which shows the solution is in CA. That is x star is in CA. And using the x star now, we also have this relation, we estimate this relation, and this with the inertial method, using the 3-point identity of Bregman. So that is what helps us to play around with the inertial point, which here is where we apply the Young modulus or the Young inequality. Because here now, we try to see how do we now work on this yn plus x star. We now see that it's only using the Young inequality. We know this is a real number and it's multiplied with 1. So there is 1 here. So using a Young inequality, we now try to transform this to be in what? In a non-P. With this, I know this is multiplying it, and this is a relation of the inertial from the algorithm, which we open the brackets, and here now we can apply the lemma of 18 and 17, and also the relationship between in order to transform this to Bregman, now apply the relationship between Bregman and norm, which we know that on P is a strongly monotone. So this helps us to transform this into this one. And now this one is from the algorithm, the inertial method. With this, we can now combine this to 24. And we have relation 26. What is our major goal? Our major goal is to establish boundedness. And with this now, we look at this, and we know that this parameter, we assume it to be in this form. And the parameter, this means that mu over n is going to 0 as n goes to infinity. And because of that, we know that there exists a positive number inside this place, which we can play around. That positive number, we can square it to come back to this place and then relate it to what we have here in 27 and get something that is so nice. So, which we call psi here. This psi here and this psi here, when you look at it, that's the problem of research, that to embed some things that people, when young ones are reading, it will be difficult to know. Here now, we pick a point psi in this point, but here we are looking at it as there exists such that what we are going to take to pick is a psi squared. So that psi squared, we now have psi squared, which is the same thing as psi dot psi, which we know that psi is less than this, the upper bound here. Which with that we can now form this relation. And from this relation, coming back to this place, we can now put it back here as a constant parameter now. And with that, we now have this. And with this now, by induction, we can now establish that mu of nabla. This is nabla here of x1, x is now less than this. And this actually shows that this ray sequence is bounded. But our goal is to show that xn is bounded. We now refer to the relationship between the brakeman and the norm. So with that, we now establish that xn is also bounded. So using that, we now use this lemma. It has been proved in sense of descent method, Banach space, and the subgradient extragradient method in Banach space, because it doesn't involve the main projection and contraction parameters in the algorithm. So if we like, we can prove it. If we like, we can just pick a lemma from the paper, cite it, and now use it. Using this and this lemma by Professor John, we now use it to try to achieve our strong convergence by putting our estimating our relation to this. And with this now, apply this lemma, we can now actually establish the next one. From this lemma, the major goal is that the lim sup of dnk is less than 0. And from here now, see that our dnk is of this form. We have known that this is going to 0. So our major goal is to establish that the lim sup of this is less than or equals to 0, which we did. And with that, we can now show that this sequence converges. But by doing that, before we could do that, we try to establish all these terms is going to 0 before we could so that that lim sup is going to 0. And with that, with all these terms going to 0,